the work I'm gonna talk about today is has been done in collaboration with your own Suvrad, or kind of like your neighbor Suvrad, as well as kind of students Haugang, Carlos Perez, Marcos Rojas, and Sanjit Shashi, and Lisa Randall from Harvard University. And so what this is mostly about is kind of trying to understand what happens when you couple black holes to some external bears. Mm-hmm. See that a crucial role in this is played by Randall-Sundrum brains, which is like a really old topic, but I'm going to use this as an excuse to spend like half of my talk reviewing old work on Randall-Sundrum brains. And then in the end, I'm going to tell you how we can use these Randall-Sundrum brains and to understand what happens if you make this external bears itself be gravitating, if you switch back on gravity in the bears. Right, why is this not working? No, I can't go to my next page. That's not good. Oh, something is messed up. Let me stop sharing and start again. And hope
that often works.
Yeah, the solution to everything in computer science is just stop and start again.
Right. It's called the halting problem. No, never mind.
From current slide. Okay, yeah, it really works. So, the big question we are trying to address is how do black holes lose information? And this is the slide I usually use to explain this to an American. So just imagine you have some sequence of words, something like person, woman, man, camera, TV, and you wonder whether 20 minutes later you still can recover that sequence of words, right? You take this information about those 5 words, you throw it into a black hole, and the question is, can you get it back out or not, right? Is this black hole able to reproduce those 5 words, maybe even the right order, extra points for the right order? Or is this information lost forever? And there has been a lot of recent progress on this, where people have been able to, in a particular context, actually demonstrate that black holes do get the information back out. And the way this has been done, people have been calculating what's known as the page curve. So that's kind of tracking some entanglement entropies and showing that it's consistent with a unitary evaporation of black holes. It's just a buzzword that says, no, yes, the information came back out. These aren't like black holes in our 4-dimensional, more or less flat space, but these black holes were special in many ways. For one, they were kind of in a box. These are black holes in anti-de Sitter space, and we all like ADS, because in ADS, we kind of believe we have a well-defined theory of quantum gravity, so we can actually calculate things. But it's more than that. These black holes were also coupled to an external non-gravitating bears. And what I want to explore with you today is kind of what the role was this bears played in this calculation. Is this kind of just a little spectator, or did the bears actually play a quite crucial role in all of this? Here are some key ingredients that went into this calculation. There's what's known as the quantum entangling surface. That's kind of some generalization of the Rutak-Yanagi prescription for calculating entanglement entropies in gravity when you also include quantum corrections. Islands were really important. Islands is a buzzword that says that sometimes if you want to calculate the entanglement entropy of something that's going on here, you have to somehow include degrees of freedom which are super far away in a completely disconnected region. So that's sort of an island. And replica wormholes also played a really important role. So I'm going to only review these concepts as they are needed. We're not going to talk at all about replica wormholes. Islands will briefly show up, and quantum entangling surfaces will show up even briefer. So we'll touch upon all of those, but I will not give you a great review about all of those things, since you can hear lots of really good talks about all those concepts all over the place. My main tool in order to address this question of how important the bears are going to be Randall-Sundrum brain worlds. And it's the Randall-Sundrum brain worlds that I'm going to spend again the first half of my talks almost exclusively on, since they play a really, really crucial role for us, right? So for one, we will use these Randall-Sundrum brains to help to resolve conceptual issues that are associated with the presence of the bears. And the other reason Randall-Sundrum brain worlds kind of got a resurgence of interest in this is that if you want to look at examples where this page curve has been calculated and you're interested in something that doesn't happen in a 2D bulk with a 1D boundary, you're interested in something where there actually is gravity, dynamical gravity, not just some trivial theory like in 2D, then you have to study Randall-Sundrum brain worlds. As of now, all these higher dimensional examples of systems where these page curves can be calculated involve Randall-Sundrum brains. Okay, so let me talk about some basics of Randall-Sundrum brain worlds. Right, this is kind of 2 decades old, but Randall-Sundrum brains have had tremendous impact on physics. They had lots of different applications. I list a lot of them here, but for us today, the only ones that I will touch upon at all is that they kind of can describe theories of massive gravity. They can give you holographic duality for conformal field theories with boundaries, and they're interesting to study black hole radiation. Of course, the last one is what I'm really after, but you'll see that the first two items play a crucial role in order to understand black hole radiation. Okay, so what is Randall-Sundrum? Randall-Sundrum is, in its essence, an answer to an almost trivial question in Einstein general relativity. You study the following theory. So you study some sort of low energy effective theory, which has as inputs in there an Einstein-Hilbert term. So you study a classical theory of gravity. It has a cosmological constant. And then the only other matter you introduce in your theory is the thin sheet with a tension lambda, right? So the only matter source you have in there is a codimension one object, the brane, whose action is given by its world volume. So today I'm only going to talk about negative cosmological constants. So instead of lambda, I'm going to have an L, which is the curvature radius of the radius 5 that you would get if the brane weren't there. And I'm also going to focus exclusively on the case where I have like a 4D brane in a 5D anti-de Sitter space. This is not any limitation. In our paper, we have many formulas for general D. It's just, in terms of talking, it's easier to say 4 and 5 than saying D and D plus 1. Okay. So how do you solve this problem? Einstein gravity coupled to a codimension one brane. So this brane is a delta function source. And if you think about how you're going to solve Einstein's equations as a delta function source, the basic strategy is something we've all seen in undergraduate class in quantum mechanics, either if you took it or if you taught it. It's the same strategy employed when you solve like quantum mechanics with a delta function potential. Recall what you did back then. So you have a potential that's only non-vanishing at a point. So away from the potential, you just have vacuum Schrödinger's equation. So you know exactly what the solutions are. They're exponentials. If you're looking for bound states, they're real exponentials. And then by normalizability, you have to pick the right one. And the way the potential shows up is you take Schrödinger's equation with a second order differential equation, you integrate it across a delta function. And the delta function then boils down to a statement that the derivative of your wave function has a discontinuity. Usually you would say that no, the wave function should have a continuous derivative, but the delta function can be integrated to give me a jump equation on the derivative of the wave function. Okay, so a delta function source in Einstein gravity works essentially exactly the same way. Let's start with by saying I want to look at vacuum solutions. So I want to look at solutions that have as much symmetry as you can imagine. Then away from the brane, there's no energy density whatsoever. I just have vacuum Einstein's equation. So I commit ADS 5 away from the brane. But what the brane does, it glues these kind of two portions of ADS 5 together in a way that the metric is smooth, but the first derivative of the metric has a non-trivial jump. And the size of the jump you get by integrating Einstein's equations across the brane. So you get a statement that the first derivative of the metric is equal to the energy density on the brane. And then the covariant way this reads is the first derivative of the metric is measured by the extrinsic curvature, and it got to be proportional to the stress energy density of the brane, which is just proportional to its to the induced metric on the brane, since my brane only had a tension, was only a sheet whose action was simply given by lambda times its world volume. What you get this way is like a Randall-Sundrum spacetime, which has like two identical copies of a part of ADS glued together along the brane. But often it's much easier to study like an orbifold of this. Many of the original Randall-Sundrum literature did this already, where instead of, you basically identify the two halves of spacetime and say, instead of having two copies of ADS glued together along a brane, I have a part of ADS 5 that ends on the brane that's terminated by the brane. So if you want to solve all of Einstein's equations, you want to have like a geodesically complete spacetime. You get two copies, but then you can impose an extra orbifold condition that truncates you down of a part of ADS 5 terminated by a brane. How does this look like in practice?
Sorry, again, Andreas, can I just ask a question here?
Yes, go ahead. I'm happy to answer. I was warned that when I talk in Mumbai, I'll get so many questions that my talk will take twice as long.
I'll try to keep the review part, my questions here to minimum. But just to ask, so you want to have this version, I guess it's called RS2, right? Is it?
Yeah, I'm talking about a single brane. Yeah, RS has these funny names. I'm talking about RS2, where there's a single brane, whereas RS1 would have two branes. So RS1 is important for like lots of the other points on my list for phenomenology and solving the hierarchy problem, yada, yada, yada. I'm just having a single brane. Well, eventually I'm going to have actually a second brane. For the first half of my talk, I'm going to have a single brane.
Thank you.
So in practice, what you're going to do, the easiest way to solve this equation is to use a coordinate system in which your space-time has this slicing. So you want to have the space-time on the brane to be maximal symmetric because you're interested in vacuum. So the space-time on the brane, what I call n, is either ADS4, de Sitter form, Minkowski form. And the easiest way of doing this is you start with a coordinate system where you slice your ADS5 in terms of this space-time n. On each slice, you have a radial coordinate with sort of orthogonal to this. And then this gets all characterized by this function a, which usually goes by the name warp factor. And then the brane is sitting at r equals to 0. And the junction condition, this jump equation, the condition on the first derivative of the metric simply becomes the condition on the first derivative of the warp factor. The first derivative of the warp factor has to have a particular jump across the brane, which is measured by lambda. And lambda has to be compared to some sort of critical value of lambda, which is just some sort of particular combination of G Newton and the curvature radius of the embedding ADS5. So let's start.
Sorry, and ds squared n is what, flat space or spheres?
Again, so n is either ADS4, Minkowski 4, de Sitter 4. These are your three options. You want to have a maximal symmetric space in the brane. And I'm going to start with the case where n is Minkowski space, and then we're going to see why I sometimes need to make different choices, need to and want to make different choices.
Okay, thanks.
So if you were to start with n being Minkowski space, then you're looking for a slicing of ADS5 in terms of four-dimensional Minkowski spaces, which is the standard Poincare slicing of ADS5, right? So you get this metric which looks something like this. You have Minkowski spaces of different size. There's a place where the warp factor goes to infinity, that's the boundary. You have a place where the warp factor goes to minus infinity, that's the IR of the geometry. Standard Poincare patch slicing should be familiar to everyone who ever done something with ADS. What the brane now does, it wants to have a non-trivial jump, and the positive tension brane wants a jump that looks like, goes from like a warp factor that goes up to a warp factor that goes down. The negative tension brane would exactly be the other way around. And you see the jump is like 2 over L basically. There's a unique value of the brane tension that gives you this. So you see that if you want to have Minkowski space on the brane tension has to be equal to this lambda c. That's why I chose this particular combination of G and L to be called lambda c. There's a unique brane tension that goes together with Minkowski space. And then the space-time that you get is twice the IR part of ADS. So you remove the boundary, you cut away the boundary and keep twice the interior of ADS, glue 2 interiors of ADS together along the brane. One thing exciting about this, and one of the things that made Randall-Sundrum famous, is that really interesting things happen if you don't study vacuum, but you study like small fluctuations around the brane. So what you want to do is you want to study linearized Einstein's equations, where you perturbed around the solution that I just described to you, this kind of 2 copies of ADS glued together along the brane. And linearized Einstein's equations give you some sort of second order linear differential equation. The way you can visualize what's happening is you change variables until this thing looks like a Schrödinger equation. So I'm talking about an analog Schrödinger equation here. It doesn't mean I'm doing quantum mechanics. It's still just classical GR, linearized Einstein's equation, just rewritten to look like a Schrödinger equation. Then you get a potential, and by just staring at the potential, you get a good idea of what the spectrum of gravitational fluctuation looks like. So you get this volcano potential where the rise, where you come, so the IR is far away in this plot. The rise is what you would get if you just had ADS5. You would get like a 1 over R squared potential from studying linearized Einstein gravity in ADS5. But then you hit the brane where you glue together those 2 copies of ADS5. So you get this like 2-sided volcano. And then the brane itself, the non-trivial jump gives me a negative delta function in that potential. That's the crater of the volcano. And just by staring at this, you can kind of see, well, if I want to analyze the spectrum, since the potential vanishes at infinity, I'm going to get this continuum of modes that reaches all the way down to 0 energy, which means to like a massless 4D graviton. But on top of this, I can also trap a bound state in the delta function. If you work out the details, you see that this bound state also gets trapped at exactly 0 mass. So the spectrum that you get of gravitation fluctuations, a continuum all the way down to 0 mass. And on top of this, a single discrete bound state, which is also massless graviton. Moreover, if you ask yourself what's the gravitational potential you would see for like sources on the brane, you would find that gravity is actually 4D. Naively, you would think, well, that can't possibly be the right. I have this massless 4D graviton. Yes, that gives me 4D gravity. But on top of this, I have this massless continuum. I have 5D gravitons, which all go all the way down to 0 mass. So they should pollute 4D gravity. But there, these flanks of the volcano potential are really important. For sources on the brain, the light continuum modes couple only very weakly to the source. They don't couple with gravitational strength. Their coupling is exponentially suppressed. So they're negligible. The heavy continuum modes, they couple strongly to the brain, but they're heavy. So at long distances, you get 4D gravity. Even so, this is a non-compact extra dimension, right? So this was not, no. People talked about this as an alternative to compactification because you get 4D gravity, even so you have a non-compact fifth dimension.
Can I ask a question?
Yes, please go ahead.
Go ahead.
So the brain is not allowed to wiggle, is it? I mean, is it allowed to wiggle in the R direction, or it's
the brain can wiggle? So there's something named the radion. In the single brain flat RS case, that radion is gauge redundant, but that's no. In general, there's a mode that describes the wiggling of the brain. And for it's really important for the other RS brains that I'm going to describe for you. The radion is dynamical, so typically you have to include a radion, but for the single brain RS case, it's kind of gauge redundant.
I see.
That's really more the wiggling of the separation between the two brains, no, Andreas?
Right. If you have two brains, that wiggling is really important because of separation of two brains. But it's for single brain, essentially. I can put the brain wherever I want. I get essentially the space-time. Moving the brain around can just be absorbed by a coordinate change.
Yeah.
That's very special to this critical brain.
Sorry,
Shiraz, can I just ask
please,
this? Then please do. Sorry. Andreas, I've forgotten some of these length scales and I'm not sure if it'll be so important. But as you said, the continuum modes do couple in an exponentially suppressed way, ultimately, right, to the 4D graviton. And does that, in a sense, mean that if I look at, sufficiently small distance scales on the boundary theory?
Right, so the only distance scales I have in my problem is basically L, right? This is classical physics so far. There's 3 Newton, but that doesn't play any role. L is the only length scale. So L separates long distances from short distances, and distances longer than L. That theory looks 4D, but at short distances, of course, it looks 5D.
Okay, and well, when we come to your black hole information puzzle, is the fact that it's actually secretly 5D. Is there some length scale where that crossover? Okay, I'll ask you again. Okay.
You can ask me then. Yes, you can ask me then.
Right. Sorry, Shiraz, please.
Yeah, no, sorry, a trivial question. I was getting confused about the wiggling and the orbifolding. If I understood right, in your unwiggled configuration, the brain is sort of like at a fixed point of the orbifold. Now, if it wiggles, it would not respect that orbifold symmetry, right? So,
right, so the orbifold will project out the wiggles. Yes.
Okay, so in this case, there's no wiggle. Yeah. Okay, great.
Yeah.
Okay, thank you.
So you cannot, whether you want to orbifold or not is up to you. In the end, most of the pictures I'm going to draw for you is probably for the orbifolded case, but it's a choice whether you want to orbifold or not.
I see. Okay, so if you don't orbifold, then what happens? What happens at the other side of the brain?
You get a second copy of ADS5. Right? The pictures I drew for you, this is not orbifolded. This is also not
so you have two,
right? I get kind of 2 copies of the IR glued together on the brain.
Okay, fine. So then you've got 2
That's sort of what the original RS paper would have done this. Many of the applications orbifolded, but the original RS paper didn't orbifold. It has just 2 copies of ADS glued together.
Okay, thank you.
Also, I'm really sorry, you must go on, Andreas, but just to say that in string theory realizations, as you know well, you don't have the orbifold.
I'll talk about the string theory realization in 2 slides, so then we can talk.
Right. Sorry.
Okay, so we are studying something in ADS, so a natural question to ask is, do we have a dual representation of this in terms of something using holography, right? So remember, the holography says that gravity on ADS5 is dual to a 4D CFT on the boundary, and this UV IR that I talked about before is just setting the scale in the CFT. So we can now look at these words that I told you. The solution we're looking at is 2 copies of the IR part of ADS5 glued together along a 3+1 dimensional brain with a massless graviton trapped on the brain. And we just translate this one by one into a field series statement saying, so I have 2 4-dimensional CFTs. These are the 2 IR regions. They have a UV cutoff because the brain removed the UV degrees of freedom. But I got this extra trapped graviton, and that isn't there in the 2 CFTs, so I need to add this back in by hand. So the holographic interpretation of RS brains is that the holographic dual to this 5D geometry is actually a 4D theory with gravity. So the 4-dimensional dual to RS branes has 2 CFTs with a UV cutoff and a dynamical graviton as part of the dual holographic description. So gravity is part of the holographic dual description in this particular version of RS branes.
And I'm really sorry, you must go on, please excuse me, but just in terms of that picture, we could think of the 2 CFTs having a stress tensor each, which is coupled together to 4D gravity with...
Right, so the 4D graviton is what gives the coupling between the 2 CFTs in this language. And here's the string serialization of this, right? If you think this is all crazy, probably this doesn't make any sense. People did come up with a top-down version of this. It's more sort of artist impression of this. But what you want to do is you study an F-serial compactification, so it's type to be on some 6-dimensional base, and there's some sort of anomaly cancellation condition which tells you there's kind of a lot of D3 branes somehow floating around, some large number of D3 branes, and this large number is set by some Euler character or something like this. But it's supersymmetric. You have moduli, you can take those 3 branes and all clump them on top of each other. And then you get a geometry like I drew on the right. The back reaction of these 3 branes will pull out an ADS 5 times S5 throat out of this complex space. But the full geometry truncates that throat. And at some point you see just Minkowski 4 times 6-dimensional base. And that's sort of what the RS brane is sort of a low energy effective description of. So that would be naturally be the single-sided version of RS, so the orbifolded version. There you have like an ADS 5 times S5 throat that truncates in some complicated tangent geometry. In that case, it's also clear that you get 4D gravity because there's literally like a genuine 4D space-time times compact 6D. So 4D graviton is definitely part of the description.
Right. Sorry, I'll just make one small comment. You must go on, just because, I mean, the slightly less mysterious than F theory on a elliptically fibered blah, 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 is simply to take type 2B string theory and consider the Klebanov-Witten background, where you have the conifold and you turn on fluxes in 2B. Okay, anyway, that's the sort of more pedestrian version. But what you say is true, yeah. Okay.
So the last thing I want to say about this critical RS brane, so the one with Minkowski world volume, is how this looks like from global ADS, just so we can compare and contrast with what I'm about to say next. So global ADS is a cylinder, and I just want to draw pictures for you. So right, this is global ADS. Every space fixed time slice is like one of these hyperbolic disks that Escher kind of like to draw, and then time just goes up to be a cylinder. And I'm going to draw for you horizontal cross sections and vertical cross sections of the cylinder. This is how this critical RS brane looks like. At a fixed time, the horizontal cross-section looks sort of bizarre, but that's not a standard feature. This is how the Poincaré patch of ADS looks like. In the vertical cross-section, you probably have seen this more often. The blue lines are lines of constant radial coordinate in Poincaré patch coordinates. The thick blue line is the Poincaré patch horizon, and then this purple line is the brane. The shaded purple region is what's cut out, right? The shaded purple region is gone. The purple line is the brane. The full space-time is whatever is left, what isn't shaded. And if you have the full space-time, you would have 2 copies of this glued together along the purple line. If you orbifold, this is the entire space-time.
Sorry, and if you look at your first diagram, you change the time, the size of that white circle changes.
Yes.
And it becomes maximal. It encompasses everything at one time, right? Or not?
It does never covers everything, right? This is sort of, I think,
I was thinking at one time it covers everything or not.
At one time you may be right. You may be right. Let me not make strong statements about this. I'm confused. We can talk about this later. Okay, but yes, it definitely, the size of the circle changes with time.
And goes to 0 at 2 ends, right? The size of the circle.
Yes. So from the point of view of the global time, the Minkowski brane has a finite lifetime, right? It gets created, it ends, and global ADS just keeps on going.
Yeah, I thought in the middle of that it covers the whole thing, but I could be wrong.
Yeah.
You might be right. Let me not make a strong statement about this. I made those plots in Mathematica and you can happily go back.
No, it doesn't matter. Yeah, thank you.
Okay, so what we saw so far is that in order to get Minkowski on the brane, I need to tune my tension to have an exact critical value. And the way you can think about this is your 4-dimensional world inherits some negative energy density from the surrounding ADS5, and you cancel it with the positive tension of the brane that you put in. And that's a very useful way of thinking about it because it tells you right away what happens if you choose a brane tension that's either bigger or smaller than this critical value. If your brane tension is too small, if you're below the critical value, then you're left with some negative energy density. If you're above, you're left with some positive energy density. You will be forced in an anti-de Sitter slicing and de Sitter slicing. And the anti-de Sitter slicing is actually the one that's going to be relevant for black holes. So that's the one I want to talk about. That's sometimes known as the subcritical brane. Okay, so what's different for the subcritical brane, right? So this time we want to study ADS5, where on the slice I have ADS4s. No, again, I write down a metric like this. I have a warp factor. This time, instead of a pure exponential, you get a Karch. And that makes a whole lot of a difference. So if you go to large values of R, right, the log of the Karch, right, the warp factor was the log of this. So the log of the Karch becomes approximately linear at large values of R. This all looks like what we had before, right? There's like my warp factor looks more or less linear. The fact when I go kind of near the boundary, the fact that my slice was curved becomes less and less important. And again, I can kind of put a brane at some position where the jump in the derivative will be compensated by the tension. You see that the derivative for the log of the Karch is always a little less than the derivative of the straight line. So that's why the tension is a little less than that critical tension. One thing that's new already here is that this time, because the slope changes, there's a unique place where you can put the brane. It's no longer arbitrary where you put the brane. And in terms of what you asked me before, this is now saying the radian would actually get a mass. There's a unique position for a given brane tension. There's a unique position where you can place that brane. It needs to sit at just the right location. But the jump in warp factor is exactly what the brane has. Nice. But what's interesting about this picture is that this time, my warp factor has a turnaround, right? Unlike the pure exponential, the log of the Karch reaches a minimum value and I go back up. So even so, my brane removed like what you thought was the UV region. Somehow there's a second UV region. There's a second boundary of this anti-de Sitter space. My warp factor goes down and comes back up, and somehow the UV is sitting both at positive large R and negative large R. So how can this be? What does this mean? In order to understand this, let's go back to these pictures. So this is how these subcritical branes sit inside my cylinder. The fact that I have ADS4 on my slice is telling me that this time the boundaries, right? ADS4 is basically conformal to a half sphere. So this time my boundary got separated into two pieces. There's one sitting at large positive R, one sitting at large negative R, and the brane only removes half of the original boundary. The brane keeps half of the original boundary around. It's the only sort of removing half of the UV because you're only removing half of the original boundary. And this has very interesting implications for holography, and to understand those, it's easier to kind of, instead of drawing global pictures, to zoom in sort of the flat region near the pole of the sphere. And then this is how this brane looks like. Right, again, so this brane is kind of hitting the boundary at some angle, and it's removing half of the original boundary. And when we saw this like 20 years ago, this kind of immediately suggested to us that this time we have actually 3 useful holographic descriptions. Right? So you can always use classical gravity in the bulk. Bulk and brane is kind of where you can calculate everything you want, right? You can use classical gravity in the bulk. But this time, if you look at this carefully, you see, well, half of the original conformal boundary is still there. So instead of having this fancy description in terms of a CFT with cutoff, the system has a dual description in terms of an ordinary CFT, that's living on a space with boundary. So there's a dual description in terms of the subcritical RS brane in terms of just a CFT with a boundary, ADS-B CFT. And that prescription has been revived by Taki and Nagi 10 years later. Same equations, same interpretation. And there's this third description. If I do what RS did before, I can be saying, well, I could interpret this yet in a different way, where I say what the blue line did, it sort of removed on one side, it kind of, I get a CFT with cutoff because I removed what my picture used to be the black, the original conformal boundary. I removed this, right? I cut out some space-time. So I get a CFT with cutoff and gravity that's living on this brane, and it's communicating with a CFT over on this true conformal part of the boundary, the leftover red part of the boundary. It can be halfway holography. Yes, go ahead. Somebody's asking.
No, maybe you complete. Let me then ask. Sorry, go ahead, please.
Yeah, so we back then sort of this is being halfway holography, where I kind of, instead of the bulk gravity, we dualized into the CFT living on the red line, but the gravity on the blue, we left as gravity on the blue. And then to go to the BCFT, the gravity on the blue gets replaced by this little defect as well. So in these days, people call this double holography because you kind of first kind of take the defect and it becomes 40 gravity coupled to a 40 CFT. And then the second step, you take the 40 gravity plus CFT and replace it by the 5D bar. In any case, you have this.
Sorry.
You go ahead.
I'm getting a little lost. Please forgive me. So, so in the case where you had ADS4 on the boundary, then you have the boundary graviton in the first place that you would have got if the brane was flat, coupled, which is present as the graviton of ADS4, right? The regular.
So that's sort of the second description. What you're talking about right now is the second description. You can think of this blue brane. The blue brane has like a 40 CFD with cutoff and a 40 graviton living on it, but it's living on ADS4. And then what's the boundary condition for this graviton on ADS4? Right, you would have said gravity on ADS4, usually I would impose completely reflecting boundary conditions. But in this particular geometry, what's happening, this blue brane actually terminates at a point on the 5D boundary where it connects with the leftover piece of this conformal boundary. So what this theory on the blue brane is, it's like a 40 gravity on ADS4 coupled to a 40 CFT with boundary conditions which say that if an excitation hits the boundary of ADS4, it doesn't get completely reflected back, but it has some transmission probability that it goes over to a non-gravitational 40 CFT, which is living on half space. So the system has three dual descriptions. One is 5D gravity, one is just a 40 BCFT with a 3D boundary, but there's halfway in between description, which is kind of one theory living on half space without gravity, coupled to a theory living on ADS4 with gravity, and they communicate with each other via some non-trivial boundary conditions.
I see.
This is what I try to say here, right? The second description is kind of interesting in that you have gravity on ADS4, but it has unusual boundary conditions in the sense that as excitations hit the boundary of ADS4, they communicate to a CFT, to a non-gravitational system, which is just a CFT on half space. And basically what you can think of this is that kind of going all the way to the BCFT, you kind of do a holographic reality on this 40 gravity on the brane, and then you just get a 3D CFT on this little defect. So you get a 40 CFT on half space coupled to a 3D CFT on the boundary.
Sorry, and in the second description, the CFT is the blue line, and all of the other space, the 5-dimensional space, is thought of as the red CFT, the non-gravitational.
Right, so right. That's right. So you have kind of a 40. It's the same, right? Originally, you had like a given 40 CFT, which was living on the entire conformal boundary of ADS5. You basically, you write the boundary of ADS5 as two ADS4s talking to each other. That's conformally equivalent to flat space. You had start, say, with n equals 4 Sylvian mills on two copies of ADS4 with communicating boundary conditions. Now you take one of those ADS4s and kind of introduce a UV cutoff and make gravity dynamical, but the other ADS4, you just have n equals 4 Sylvian mills as it used to be without any gravity.
Right. So, but just to say again, so in the gravitational picture is very clear, and when you sort of apportion degrees of freedom between the non-gravitational CFT, the gravitational CFT, the cutoff gravitational CFT, very little is given to the cutoff gravitational CFT. Right?
Yeah, roughly speaking, I would be saying like the left half of space-time should be like the red CFT and the right half of space-time should be the blue CFT, and because the right half got sort of truncated, the blue CFT has a cutoff. Right. That's sort of some sort of vague sense. No, in the end, the 5D gravity captures the entire field.
Yeah. Of course, yes. Okay, thank you.
This is what I just talked about. So what's exciting about the systems, you have these three descriptions. They do three very different things for us, right? The classical 5D system is solvable. Everything you ever wanted to calculate about the system, you can solve in the 5D system because all you're doing is like solving classical equations of motion. The BCFT description is the one where you really know what you're doing, right? That's a well-defined quantum system. It's UV complete. It's just a field tree. There's nothing to want. There's like everything you ever wanted to know. In principle, is well-defined there, right? No question about like UV completion. And in between is the strangest part, like this gravity coupled to a CFT communicating with this other CFT. But that's exactly what you need for understanding black holes coupled to a bath, because you have the system that you have quantum gravity living on this blue brane, communicating with this non-gravitational bath on the true boundary of ADS.
Andreas, just to get the various scales right, in the second description, let's say there is the 4-dimensional Newton's constant characterizing gravity in ADS4. The communication of the gravity in ADS4, that part with the non-gravitational CFT Is that through operators suppressed by the Planck scale, or how does
It's
that?
via boundary conditions, right? It's via boundary conditions. It's order one effect in the boundary.
Okay.
You have scalar fields, right? In terms of gravity, it gets communicated to gravity via loops, but in terms of the matter, in terms of the CFT on the brane, it's an order one effect, right? Usually you would say the boundary condition of a field in ADS is that its leading coefficient has to vanish. Its subleading coefficient is it's undetermined, right? That's how we all learned ADS CFT. Here, the boundary coefficient is that the leading term of a scalar field on the blue brane is equal to the leading term of the scalar field over in the red part of the CFT.
Okay, I got it. And the gravity, of course, is only on one side, and then those effects are some.
Right. So if you ever kind of were in a situation where you wanted to study gravity coupled to a bath via boundary condition, which is exactly what all those people did who studied page curves, then Randall-Sundrum branes give it to you for free.
Thank you. Very nice. Beautiful.
Okay. I'm completely running out of time. I hope you don't expect me to be done in 20 minutes. But
no, you can go. Abhijit is the boss, but you can go much more. I think he'll say.
Okay, so what happens to the fluctuation?
Don't worry about that.
Right? So here was sort of this picture that I showed you before in the critical case, right? This was the volcano potential when my brane had like a Minkowski world volume. So what happens if I bring back in this second boundary, right? So what was different in the subcritical case, I got a second boundary, which is telling me, now I can draw analytic pictures, but roughly speaking, you put this whole volcano potential, you put it in a box because my volcano potential shoots off to infinity again, far away from the brane. And there's two really important things to these gravitational fluctuations. For one, this continuum that we saw before gets broken up into discrete. That's not what I want to focus on. What's even more exciting is that I get the zero mode that was at zero mass sitting at the bottom of this kind of volcano potential gets pushed up a little bit by being put into a finite box, so that trapped graviton on the 4D brane is no longer massless, it actually becomes massive. Back then to us, this was exciting because it's the first example of a consistency of massive gravity. By now we have those, a dime a dozen. But let's try to understand a little better how this happened. Why did this graviton and mass? I want to understand the graviton mass in both the other dual descriptions. So this is like the 5D classical bulk calculation says the 4D graviton on the brane gets a mass. Can we understand this from this halfway dual, 4D gravity coupled to a CFT with weird boundary conditions? There was a beautiful calculation done by Ferrati. He said that's exactly what happens if you do that. If you calculate this diagram where you have a scalar loop coupled to a graviton, you might think that's sort of a one loop correction to the propagator of the graviton. Maybe that gives the graviton a mass, right? You just do that calculation, you find indeed that diagram in anti-de Sitter space gives the graviton a mass. Why haven't you heard about this? It depends on the boundary conditions of the scalar field. Well, maybe you've heard about this, you should have. That's not a beautiful paper from 20 years ago. But most people haven't heard about this. And the reason for this is that if you impose the standard boundary conditions for the scalar field, that it reflects off the boundary of ADS4, that it's known. Leading term vanishes, the subleading term is kind of free, then you don't get a mass. But for any other boundary condition, anything that allows some fraction of the scalar field to communicate to something that's living behind the boundary, in particular in this case that we studied where these two CFTs communicate, you always get a graviton mass from this one loop diagram. And you can make this very quantitative. You can kind of in cases where you have like two ADSs communicating with each other via a double trace deformations, because that models the boundary condition. You can do it, calculate this graviton mass exactly both in the bulk and in the boundary, and get a beautiful matching between conformal perturbation tree and the one loop calculation in the bulk.
I guess any boundary condition that breaks the conservation of the stress energy, right?
Good. So yes. Okay. So this was the halfway dual picture. How do you understand this from the BCFT picture? And there,
sorry, Andreas.
It's even easier, right? From the BCFT point of view, basically just look at this and ask yourself, what is this 4D graviton dual to? This 4D graviton is dual to the 3D stress tensor living on the boundary of the BCFT, on the 3D defect, that's the boundary of the BCFT. So if you have a BCFT and ask myself, is the 3D stress tensor conserved that's living on the boundary? It's not, right? Because the 3D stress tensor communicates with the 4D stress tensor. What's conserved is the 4D plus the 3D stress tensor. There is a conserved energy density in my BCFT, but the T3D alone isn't conserved. So it can, and in any interacting theory will, pick up a normalist dimension. That's the graviton mass. And again, you can also calculate this explicitly in string theoretic models. So we did this for like the D3D5 system. We explicitly calculate this in normalized dimension for a conserved current instead of the conserved stress tensor, but we thought that's good enough. So, and this is a very general story. So I told you this for RS branes, but this connection you can make quite generally. Whenever you study massless graviton in ADS, it's dual to a conserved stress tensor. But if for some reason, say you want to calculate a page curve, you want to study ADS gravity coupled to a bath, that's automatically telling you that the dual the stress tensor dual to a graviton is no longer conserved. So it can, in any interacting theory, will pick up in a normalized dimension, you end up with a massive graviton. So you can't have one without the other. The moment you couple ADS due to an external bath, you study a theory of massive gravity. So in short, what I'm basically telling you is that all these page graph calculations that people have been doing in terms of gravity, ADS gravity coupled to a bath, they all happened in the theory of massive gravity. And so this is the recap so far. The old work, subcritical RS brane realize ADS gravity coupled to non-gravitating baths. They're beautiful because they have a dual interpretation in terms of a BSCFT. And the general lesson you should take away from them is that ADS gravity coupled to a bath is a theory of massive gravity. You won't know much about the massive graviton and other people talking about page curves and islands. So the real question is this important? I think there will be lots of people out there who tell you that's sort of just, that's true, but doesn't really matter. You calculate page curves, but the question is, is the fact that this graviton is massive in the setting, the fact that we couple to an external bath, is this just a harmless spectator, or does it actually change the physics?
Could I ask a question?
Yeah.
So I agree that in the East Coast model, this feels like it's important because they have an explicit transparent boundary condition between the CFT and or the gravity region and the bath region. But in the West Coast model paper, they don't actually have transparent boundary conditions, right? They just consider sort of an entangled state between the black hole and the radiation. So is this massive graviton stuff important for the West Coast model, or is it not?
The bath needs to couple to the gravity for me to get a massive graviton. So you can ask yourself what you want. There are lots of papers where people get islands where they have a bath that's completely decoupled from the bulk. And they do get like islands in that case, but in this case, you would never be able to recover the information, right? If you want to know how does the information come out of the black hole, you need to couple your bath to the bulk and you get a massive graviton. Once the information is all out, you can say, well, now I can switch off the interaction between the two. I have this radiation region, which I define in this decoupled bath. And now I can find islands and all the information is out there without having any coupling anymore. But I think this is sort of fake because you said, okay, here was my black hole. I wait till all the information comes out. Now I take a decoupling and now I can find my information is outside. But the interesting piece is how did the information come out? Not how do I describe the system once it's out and I decoupled. I took away the opportunity for information to come out. So I think if you use a non-gravitational bath at all to solve the information paradox, you're necessarily stuck with massive gravity.
Okay, thank you.
Andreas, there's one thing not clear to me. Thanks for a beautiful presentation. But just to ask, ideally, one wants the bath to be in asymptotically flat space, because at least that's when the information question is clear.
Let's hold on for a few minutes, since this was sort of supposedly the review part of my talk, and now I want to talk about the most recent work where we address part of what you're talking about.
Okay, but just to flag the question, then please, whenever, which is if your
let me just show you this space, right? So the question is, does the graviton mass matter? What you really want to know
is there even a graviton mass if the bath is in asymptotically flat space?
Right, so let's talk about asymptotically flat space, right? So what happens in asymptotically flat
Andreas,
space is that, yes?
Sorry, before, I have a small question, just to understand this better from the last slide. So when you say, when you couple gravity to a non-gravitating bath, you would end up generating mass for the graviton. So is it important that this coupling be to non-gravitating bath for the graviton to generate the mass?
Yes, and we will soon see in like 5 slides, you'll see that if I couple to a gravitating bath, I get a massless graviton.
Okay, thank you.
See, if I look at this picture, right, if here I have like the reason the 3D stress tensor isn't conserved is because it's kind of conserved is the stress tensor of the 4D bears and the 3D stress tensor. If you put gravity back in this bears, now you have a holographic dual with just the 3D theory, right? Say if this left-hand side, the T4D, is also living in a gravitating ADS4. If I have two gravitating ADS4s which meet at a 3D defect, now my holographic dual description is no longer a 4D CFT living on half space with a 3D boundary, but it's just the 3D boundary. Takeyanagi calls this wedge holography. And in this case, now all there is to my universe is this 3D stress tensor, and now it's conserved again.
And
like
that is supposed to be dual to the entire 5-dimensional system.
Yes, now we have it. That shouldn't be surprising because in that case, I have like my 5D system is a finite interval times ADS4, right? You are not concerned that like the dual of a 10D geometry, which is ADS5 times S5 is dual to a 4D CFT. Same here, like ADS4 times interval is dual to 3D CFT, not a 4D CFT.
Yes, thank you.
We'll talk about wedge holography also in a moment.
Thank you.
Back to flat space, right? What we really want to know is what happens to information of black holes in asymptotically flat space. And Suvrat, who's hopefully still out there together with his collaborators, have this claim that if you study black holes in asymptotically flat space, something completely different is happening. Instead of getting a page curve where information first gets lost and then comes back out, you can recover the entire information of everything that's inside space-time from like the paths of future null infinity, like this little red region in this diagram, which I stole from Suvrat, that supposedly contains the entire information of the quantum state inside. And that's, Suvrat can give you a very precise operational procedure what you should do. If you're an observer, like an asymptotic observer in flat space, you measure the exact gravitational field at infinity, you can deduce the exact quantum state of what's going on inside. So you never lose any information, whether that stuff falls into the black hole or not is completely irrelevant. You always know the exact quantum state of the system just from measurements at infinity. That's why you get these flat page curves. That looks different from what people tell you who calculate page curves in ADS coupled to a burst. And this is sort of what Suvrat said at Strings. This is how our project got started. When I heard Suvrat say those words, Suvrat said, the difference between what they did and what he's doing is that they have no gravity in the bears. And if you want to think about asymptotic flat space, it's like if the bears itself were gravitating too, right? In Minkowski space, it's not like gravity stops at some finite distance from the black hole and then you have a non-gravitating bears. Gravity is everywhere. So this asymptotic observer is still living in a weakly gravitating system. So if you want to understand the page curve in asymptotically flat space, a much better model would be coupling this ADS black hole in a box to a bears, which itself is gravitating. And this was the prediction that I saw Suvrat make at Strings, is kind of saying, if you bring back gravity in the bears, you should get a triple page curve. And that got us all very excited because this is something you can easily test by using RS branes. Yeah. So that's the goal for my last 8 minutes, is to kind of tell you what happens if you use RS branes to bring gravity back into the bears.
So, but if there is a weak gravity in the bath, wouldn't it back react and create a cosmology?
Yes, we avoid this by doing some fancy games, but yes, in principle, that you have to watch out, right? If you want to, if the radiation comes into this weakly gravitating region, it will make this weakly gravitating region not be Minkowski space, right? Yes, that is absolutely correct. And you'll see this show up later. So now I have to tell you how to actually see islands in our S-branes, and then we can wonder what happens if I switch on gravity in the past. Okay, so this is what people did when they found islands in exactly the setting. Right, one key ingredient in this black hole evaporation was this quantum entangling surface, which all this is saying that you get important contributions from matter, and that's great because in the RS branes, matter contribution to entanglement entropy for the 4D universe get all encoded in classical 5D geometry. So using RS branes, you automatically can deal with quantum entangling surfaces because the classical 5D RT surface include all quantum corrections on the brane. So if I want to study this whole system in RS systems, all I ever need to do is study classical gravity, and the 5D classical gravity automatically tells me everything you want to know about like 4D gravity coupled to a burst. But the problem with this is twofold. For one, classical 5D GR is still hard, right? If I want to solve a full time-dependent evaporation of a black hole, this is like nonlinear PDEs. I don't want to touch this. The other thing it's known in ice brains that sometimes the Hawking radiation that comes out of a black hole is order 1 in the large n counting instead of order n squared. It sometimes happens that the presence of the black hole itself drives the CFT into a confining phase. So even though the black hole has to Hawking radiate at a temperature that is set by the Hawking radiation, the energy density that comes out is order 1, not order n squared. That's a problem because we don't want to do quantum corrections, right? We just want to do classical gravity. Fortunately, it's completely understood when this is happening. This goes by a story that has names like funnels and droplets. And all you need to know is that funnels good, droplets bad. Funnels means you see the Hawking radiation in classical DR. And we know when we have a funnel and when we have a droplet. The second problem is more real. And the way people found in order to get around this, they do the following, right? So you want to study ADS gravity coupled to this non-gravitating burst, and you want to see a black hole in the ADS sort of evaporate and the radiation go over to the non-gravitating burst. That's a time-dependent process. We don't want time dependence. So what we do is we take this non-gravitating burst and we heat it up to a finite temperature, which is equal to the Hawking temperature. So now the eternal black hole remains eternal. Everything is kind of nice and time independent, but there's still communication between the black hole and the burst. You would still say radiation comes out of the black hole and goes over to this non-gravitating burst, but there's also radiation that comes back from the finite temperature and the burst and goes into the black hole, and everything's in thermal equilibrium. The claim is in this case, you still have an information paradox, and the same techniques that allowed people to calculate page curves in the time evolving lower dimension systems can also resolve the slightly simpler information paradox that you see in this case. To understand this information paradox, you have to go back to some old work of Hartmann and Maldacena, which told you, like in this internal black hole geometries, whenever you calculate an entanglement entropy between something that's happening on the right and something that's happening on the left, so in the thermal field double, then if you take the natural time evolution, which goes up on both sides, which is some sort of non-trivial time evolution in the system, any sort of entanglement entropy of that sort will grow linear in time because the RT surface has to go through this middle of this fully extended geometry. There's an Einstein-Rosen bridge that connects the left and the right of the Penrose diagram. And you just look at this red line, as I pull it up, it gets longer and longer and longer. And if you do this, no, if you calculate it, you find this is a linear growth. The length of the RT surface, or the area of the RT surface, grows linear in time because the linear growth of the Einstein-Rosen bridge. And the puzzle here is that when you calculate sort of any entanglement entropy in a finite temperature system, you somehow think that S black hole, or the Bekenstein-Hawking entropy of the black hole should somehow give me some saturation. There shouldn't be entropies that are bigger than that. So if you look at this Hartmann-Maldacena surface, it wants to grow forever, but you would expect that unitarity kind of tells you the entropy shouldn't go past the Bekenstein-Hawking entropy. And to begin with, that's fine, but eventually you outgrow the Bekenstein-Hawking entropy. That's your information paradox.
Sorry, Andreas?
Yes.
Sorry, can I ask a question from before, just to understand this mass of the graviton a little bit better? Okay. So from the CFT point of view, can I think of this statement as a statement saying that if you have a conformal field theory with a stress tensor and couple it to another conformal field theory without a stress tensor, the resulting theory should not have a conserved stress tensor?
This was the statement, right? So if you study an ADS4 that's dual to a 3D CFT, and that 3D CFT is coupled to anything else, then what's conserved is the energy of the 3D CFT plus whatever it coupled to, right? What's conserved is the tensor of pairs plus 3D CFT, not the stress of the 3D CFT. And therefore, the graviton that was dual to the stress tensor of the 3D CFT gets an enormous dimension. Gets a mass because the dual operator.
But if the non-gravitating bath were not a 4D CFT but rather a 3D CFT itself, would this have
be the same story,
alleviated
right?
the problem?
So as long as you have any coupling to any bath, this is the case, right? Any coupling will make T3D not conserved.
Okay, thank you.
There's a paper that, like, by Ofer Aharoni, myself, and Adam Clark, where we did the following. We studied like 2 ADS5s. Each one is dual to some 4D CFT, and you introduce a double trace coupling that makes the two communicate to each other. Then you can explicitly say, so you have basically both, you have a 4D CFT, another 4D CFT, and you couple them to each other by double trace coupling. In this case, you also get a massive graviton. And again, this is the case where we calculated this mass of the graviton by this one loop calculation in the bulk. And we also calculated in conformal perturbation theory, and you get like beautiful matching on both sides. It's like tour de force calculations on both sides, they look very different. You get like a beautiful matching between the graviton mass and the bulk and the anomalous dimension out on the boundary.
Thank you.
It was sort of 40 bars with 40 CFT. But it's this general structure that any coupling to a bar, so the stress tensor isn't conserved, so you get an anomalous dimension, so you get a mass.
Okay.
It's not crucial to me that the bars was a 40 CFT. The bars can be anything that takes energy away.
Okay.
I think this is really a very general picture. You couple to a bars, that means the stress tensor is not conserved. You get an anomalous dimension, you get a massive gravity. And up there was this paper that I just talked about. Where was I?
Sorry, but just sorry. I mean, just to understand this. I mean, if you have two CFTs and you couple them, you could imagine a flow leading you to another CFT with conserved stress tensor, right?
So in this system of two CFTs coupled with each other, you started out with two, right? You had two ADS5s. You started out with two massless gravitons. And after you couple them to each other, you're left with one massless graviton, which is sort of shared between the two ADS5s and one massive graviton. So when you say you can imagine there, so there is one massless graviton left in the system, but not two massless gravitons.
Right, but you just need one massless graviton, right? I mean, why do you want it the other?
So, but in this system right here, we have this 40 graviton, the 40 graviton dual to the 3D stress tensor will pick up a mass.
I see. So there was a specific graviton that was coupling, that was doing all the Hawking this thing.
That's right. The graviton that you study in this case has a mass. Yes.
Yes. Thank you.
Yeah.
Somehow, I know you'll come to this, but at least the string theory constructions I have in mind with various RS throats where you'll get the double trace stress operator T mu over M blank. I mean, it seems to me in flat space you won't get
about string theory constructions. I think so. The string theory constructions look very different for the subcritical RS branes than for the critical one. The ones you're describing, you're back in kind of critical RS branes with like Minkowski brane on them. If you want to think it string theory embedding, think these papers. Where did I have them?
You're right. I'm thinking.
Good parallel.
I'm thinking
there's a large class of literature which goes by the name supersymmetric Llanes solutions, but hiding in there are supersymmetric solutions for these V branes ending on S5 branes. And these are the relevant top-down descriptions you wanted to have right now. And they basically look exactly like my pictures, where instead of the RS brane, you basically have like inside ADS5 times S5 certain cycles shrinking to 0 size because they're wrapped by 5.
You're right. Yeah. Okay, you're right. Yeah, I had in mind the critical one. Yeah, you're right. That suggested no mass, but you're right. Yes. Okay, go ahead.
Yeah, so in the critical one, there's no mass. That's absolutely right. But in the subcritical one, you also get a mass. Like Costas-Bacchus calculated fluctuations in those cases too, and you did get a mass in those cases.
Good. Sorry.
Okay, so here's basically the one plot that if I'm able to convince you what's happening on this plot, you understand exactly how people got islands out of our S branes. So this is kind of the one plot you need to understand, and then hopefully my entire talk makes sense. So here, to begin with what we had before. So we have this brane, which it's left-right is flipped because I copy-pasted from a different paper. But no, the blue is the brane, and it cut out like part of ADS5, including this black original part of the conformal boundary. The red is this non-gravitating bars, the part of the true conformal boundary that's the left, right? So we have the description we're after. There's like gravity on this blue ADS4 brane coupled to a CFT, and there's a non-gravitating bars with a CFT on the red boundary. What we want to do now is study a black hole. So we need a horizon. What I want to do is I want to have a geometry. There's a black hole which intersects the brane. So you see over here, this black dashed line is a horizon. It intersects the brane. Indeed, we put a black hole on the brane. Furthermore, I told you in order to keep this static, I want to send this non-gravitating bars to a finite temperature. So I also need a horizon on the right-hand side of my picture. That's just a standard planar ADS5 horizon, which is saying my non-gravitating bars is at a finite temperature. Now, what makes this a funnel is that those two horizons are connected with each other. So really, it looks like I just have one big black hole in the bulk, but you should think about the type, the horizon on the left, where the horizon intersects the brane, that's the black hole in the brane. The part on the right is just telling me the bars is at a finite temperature. Now I want to go into this bars and identify part of this bath, what I marked here in green, as the radiation region. So that's far away from the defect. And in these page curve calculations, that's sort of what people say, well, once radiation reached this green region R, it really came out of the black hole. That's sort of the stand-in for the far away Hawking radiation. And what you want to do is you want to calculate the entanglement entropy of this green region R. So you want to find RT surfaces that determine the entanglement entropy of this green region R. Well, one thing you can do is you can just draw this line that goes vertically straight down into the horizon. And this is this Hartmann-Maldassena surface that I showed you before. It looks like completely time independent here, but now what's behind the horizon is this Einstein-Rosen bridge and then eventually the thermal field double. And because that Hartmann-Maldassena surface crosses the Einstein-Rosen bridge, it will have this entanglement entropy. It will have an area and hence entanglement entropy which grows linear in time. What's new now, the new opportunity the brain gives you is the second RT surface, the ones that I labeled by island. It's really not like an RT surface associated with an island. So it's not like the green dashed line is the island, but the green line gives rise to an island. And that thing has a constant entropy because it doesn't dive through the black hole. It's entirely sitting outside the black hole. And what's the island is this region on the brain, maybe I should have marked it in color, that's sort of between where the beyond where the RT surface ends. And what this is now saying, there's some degrees of freedom on the brain, including the black hole and everything that's between the black hole and the endpoint of the green surface. These degrees of freedom, they sort of secretly belong to the radiation region in that sense that they're also cut out by this RT surface. And what's really important about this picture is that this boundary of the radiation region, right? You do this in the non-gravitational bath. That's completely up to you. You tell me, like, here's a CFT living on half space, and I go like 5 steps away from the defect, and I decide here starts the radiation region. If you feel like it, you can do another step, go 6 steps away, and say, no, now I started here. That's fixed externally in the non-gravitational region, completely up to you.
So
at the end point,
and the island region includes points outside the event horizon.
Yes, yes. In this case of these systems on our S-branes in dimensions bigger than 2, you always find islands outside the horizon. The paper by Maldassena that first did this had this even in the title. I think it said islands outside horizon. But yeah, the island includes the entire black hole and then part of the blue brane that's between the endpoint of the green dashed line and like everything that's beyond the endpoint of the green dashed line is the island.
Okay, thank you.
Andreas,
the island doesn't have to be inside the black hole. The island contains the black hole, but it contains more.
Yeah, sorry, I was also confused about that. Let me just ask you, if I were looking at everything, projecting it to 4 dimensions, that is on the boundary, right? Then it's true that you have the black hole inside in the gravitating region and the boundary, which is your red dot, which is of course not inside the black hole horizon. And then you have the non-gravitating green region. And now if I think of the island, it involves some part which goes from the quantum extremal surface leftward in your diagram and your green region in solid. Is that correct?
The green region in solid is what I want to calculate the entanglement entropy of. That's not the island, right? The island is, I believe, this. You can see my mouse, right?
Yeah, it's not the island, but the island prescription would add that part to the entanglement, right?
The island prescription is saying that sort of this green surface calculates the entanglement entropy of the green region, and therefore the degrees of freedom that are sitting in here are somehow redundant with the degrees of freedom that are sitting in the radiation region. Somehow, if I want to calculate the entanglement entropy of this green region out of the boundary, that region in here also counts in the sense that the homology constraint is sort of something that this thing is, including that blue region down here.
Yeah,
sort of.
I answer, but please bear with me. Let me get my head screwed on straight, because let me just understand first what your 5D situation would have meant if I were just looking at it in 4D, okay? And in 4D, if I understand right...
What do you mean by 4D? You mean the BCFT description?
I mean the 4-dimensional description which you are showing as a line at the very top, if I understand, which has...
Right, so I have two descriptions which you could call 4D.
The mix
is 4D CFT living on half space with a 3D boundary, and the other is like 2 4D CFTs, one without gravity, one with gravity, communicating via their common boundary.
I meant your last one, what you call the mixed description.
Right, okay, yeah, good. The one with gravity to the bath. Yeah, in terms of that 4D description, I'm describing a black hole in ADS4 and coupled via transparent boundary conditions to a non-gravitating bath held at the same temperature as the black hole.
Right, good. Now, the gravitating part has a quantum extremal surface.
Right, which is the endpoint of that green surface that's sitting right here.
But the endpoint in 4 dimensions.
Yeah.
And that extremal surface is way inside where your red dot is, the boundary between the 2 regions.
Yeah.
Is that right? And then the island prescription would say keep the region to the left of the quantum extremal surface plus the region outside to compute your
right. So
entropy.
what's left of the quantum extremal surface, that's the island. That's why everything that's in here, that's the quantum. It's the island. This is the quantum extremal surface.
So, Sandeep, just to clarify, in this, this is just the usual Ryu-Takenagi prescription that Andreas is drawing here.
I understand. I just want to make sure I understand it first as an answer to a 4D question, which I would have.
So from the 4D point of view, this quantum extremal surface. Sorry, the quantum extremal surface contains like the matter part, and that's sort of why you draw a 5D Ryu-Takenagi surface, right? The 5D Ryu-Takenagi surface. That's what you're supposed to do for a quantum extremal surface, includes the matter contribution as well as the gravitation contribution.
So you are saying that the answer to that 4D question, which is this 5D RT surface, partly lies already outside the, includes the dashed line.
Yes, it's the quantum extremal surface is outside the black hole. And again, this is not our work. This is like Maldacena found this, and he put this in the title of his paper. This is when people study this particular scenario that was, nobody told you the quantum extremal surfaces have to be inside black holes. They can be inside, they can be outside. You minimize, and in this case, minimization tells you it's outside.
But I mean, in 4D, it would have been inside, but your 5D construction brings it.
No, this particular system where you couple to this finite temperature is always outside in all dimensions.
Even in 4D, I mean, even in the boundary theory, it would have been outside.
I'm not sure what you mean in the boundary C, but if I do this with ADS3 brane and ADS4, it's also outside.
Okay, Sandeep, to think of the 4D picture, maybe what you should do is you should ignore all the white part, look at the blue solid line, the red solid line, and the green solid line. And so
for an eternal black hole coupled to a bath, this is always the case.
No,
the island is outside the
sorry. Sorry, I should let you go on. But in the 4-dimensional picture, you have the brain, your blue line, I thought just demarcates the gravitating from the non-gravitating.
Exactly. So the island.
Now, the 4D picture, this is what people just try to tell you. The 4D picture is only what's living on the line, right? The 4D picture is like a gravitating line and a non-gravitating line. That's the 4D picture, right?
No, the 4D picture I want to use is 4D gravity. You can have a CFT coupled to 4D gravity.
Okay, that lives on the blue line, right? The blue line is the 4D region with a CFT coupled to gravity. That's the entire blue line. That's the 4D region.
That's what it is in your picture. What's the black line?
The black line is sort of the original part of the boundary that got removed by the brain, right? The shaded region is all gone. The black line was the original ADS5 boundary. And then I put in the brain and removed everything that's shaded, and then it's living on the blue line.
Okay, I'm sorry. So even in the picture, which is blue line union, everything else, the quantum extremal surface would have lain outside.
Yes.
I didn't realize this. Okay.
Again, that's an old result that not even ours, but that's a fact. Like in this eternal black hole coupled to a finite temperature bath, the island is outside.
In the ADS2 case, I think you can do it using CFT2 technology, and I think it is reliable. Even in ADS2 coupled to a heat bath.
Right. In ADS2, people have done it both ways. They've done it using this double holography, and they've done it using like
Merolf et al. The quantum extremal surface lay inside, right?
That's an evaporating black hole.
Finite temperature and the
that's an evaporating.
Don't look at the eternal case.
Okay. Evaporating as opposed to heat bath. Thank you. Okay, I'm with you. Sorry, please go ahead.
Sorry, Andreas, just the previous translate, just one more question. the region behind the in the island, can it causally communicate with the red region, or is it sort of causally
This is sort of a finite time slice. Yeah, as time goes on, yes, this can causally communicate. Right, signals can go to the boundary of ADS in a finite time and communicate to the boundary.
Okay, so then if you move the intersection between the red and the green line off to infinity, then presumably the island starts going nearer and nearer the event horizon, or maybe below. Is that right?
Yeah, yeah, it goes nearer and nearer and nearer.
Okay, so otherwise that would violate causality, because you could,
sorry, just
because you could do something in the green region that would affect space-time here, and then that could communicate to the red faster than a signal could go. So
yeah, no, the island drops down deeper and deeper in the bulk as you make the green region.
Sounds good. Thank you. Yeah.
one question.
Just once more. Sorry, where is the event horizon?
The black dashed line is the event horizon.
No, in 5.
4D event horizon is where the black dashed line intersects the blue line.
So it's as time goes by. What was the answer to Shiraz's question? Does it?
I think he said
this is static. This is completely static. As time goes by, nothing interesting happens.
So I
was wondering what happens if the signals that you try to shoot out.
See, if the intersection between the red and the green line is taken to infinity, and this picture remained unchanged, there would be a contradiction, because then you could do something in the green region, which is infinite, very far from the red region, but the bulk would then be able to communicate to the red region in finite time. And Andreas was saying that, okay, as you take this intersection between the red and the green off further and further, the dashed green line goes down. So
okay, yeah, that's what you'd expect.
Yeah, okay.
Got you. Thank you. Sorry, please go ahead.
Sorry, just one.
So this is the picture that you get now. If you look early on, you find that the Hartmann-Maldacena surface has a.
Sorry, Andreas, can I ask one question on the previous slide? So I wanted to do the opposite of what Shiraz wanted to do, wherein I bring the red interval smaller and smaller, right? As it approaches the red dot, even then the island should not come very close to the red dot, right? Because
the island shrinks into like some infinitesimal surface. It does shrink into something infinitesimal. The island kind of completely shrinks towards the red dot. That is happening.
No, but should it not remain always on a finite distance away from the red dot? Because you are simply
it's both. I mean, they shrink together. They shrink together, right? As you go, this is kind of completely scale invariant picture. So there's once I get closer and closer to the red dot, I can forget the black hole. It's like an empty ADS. In empty ADS, scale invariance is basically telling me there's a unique surface where like the position on the blue brane and the position on the red brane, they're proportional to each other. So if you make the green region kind of end up epsilon away from the red dot on the right, then the island ends up epsilon away on the blue line.
No, but even if it is epsilon away, then I'm simply computing, let's say, entanglement entropy of the radiation, right? And why is the radiation able to see the entire bulk? I mean, I thought it would still be a finite distance away, even though
it's not. I mean, I can tell you properties of the RT surface. It's not. As you push the radiation region into the defect, the island also gets pushed into the defect.
I see.
Is there, okay, you have to go on, but and I should be better informed. But isn't there something almost contradictory in the quantum entanglement wedge lying outside the event horizon? I can send signals from the event horizon out to the boundary and reconstruct the region in between, but you say the entanglement wedge doesn't even go into that. I mean, it almost seems. Anyway, go ahead. I have to proceed.
Yeah. You should invite Hartmann-Maldacena and ask him those questions.
Fine. Okay. Yeah. No, thank you. I'm sorry to be so poorly informed. Yeah. Go ahead, please.
Yeah, so
it's not like if you were to take this and the union of the region on the other side, the entanglement wedge is everything below the green dashed line. So it's, I mean, in this case, it probably ends at the horizon, but if you were to take also the other side, so you can see inside the horizon. I don't know if that was your concern. Why does the surface have to be always behind the horizon? Like, what is it that tells you that?
Well, if it's outside, isn't there a region between the horizon and the quantum entanglement wedge, which you cannot encode for on the boundary?
Yeah, which you cannot encode for using only the red part of the boundary. But who tells you that the red part of the boundary has to describe everything? I mean, this is some CFT which has been coupled forever, right? I see. So your concern is that if you just take the blue region, the blue in 4 dimensions, you would have thought the red dot should describe everything.
Red part is not even in the boundary, right? Isn't the boundary of the gravitating region the red dot?
So you're saying your concern is why isn't the red dot describing the entire blue solid line? I guess that's your question.
Yeah.
Right, but that goes back to what we had before, because the red dot alone is not a unitary description, right? The red dot it has a non-conserved energy density. It leaks into the red region. The red dot alone is not a consistent description. The red dot is a 3D boundary of a 4D BC, and they come together. The red dot alone is not anything. The red dot alone is just an open path subsystem of a consistent, CFT on half space.
I see.
It's also been coupled forever. It's an eternal black hole.
Yeah.
It's been coupled forever. So that's why the information is kind of delocalized between the red and the.
Okay. I hear you. Thank you. Go ahead.
I have one last question about this previous slide. Sorry to interrupt again. If you were to use the quantum extremal surface prescription on the blue line, like you're in the intrinsic 4D perspective, would the fact that the graviton is massive be important? Like, would that massive graviton give some extra contributions to the quantum extremal formula?
I don't think so, because both of them, right? So the mass of the graviton, the way Paradia understood it, it was due to the quantum effects. So what's living on the 4D brane is sort of gravity coupled to a CFT, and the mass comes from the loops of the CFT, right? So it's the bulk captures. So this is when we calculate the quantum corrections of the CFT explicitly by doing like 5D classical calculations. We don't need to separately include the mass. The mass is sort of an output of the quantum corrections due to the 4D CFT. It's not something, if you add a mass by hand on top of it, you sort of double count the quantum corrections from the CFT.
I see, but so it doesn't even change the wall-like term in the entropy formula, like the area term.
No.
Yeah. Okay.
Basically, not like these 2D calculations, the quantum extremal surface is completely dominated by the matter CFT. It's
I see. Okay, got it.
The green surface is calculated.
Thank you.
So this is my 20th attempt to show you this slide. This is just saying, if you believe this page before, then this is the picture that you get. The Hartmann-Walder-Sehner wins early on, but it grows linear with time. The island surface has a larger area, so you would think it's subdominant, but because Hartmann-Walder-Sehner grows and the island doesn't, at some time you get this crossover and you saturate at the entropy saturates because of the island surface.
So, sorry, this is a slightly technical question now that you've completed your slide, sorry, which is, do you have two quantum extremal surfaces and one is the global minimum, or is it that you just have the island global, island quantum extremal surface at late enough time? I'm just curious.
The Hartmann-Walder-Sehner surface doesn't have any island, right? But I have like the RT surface, I have two saddles for the RT surface and one takes over from the other, right? It's
okay,
the one
so you actually get two saddles, huh?
Right, like these two lines that I have here, right? The Hartmann-Walder-Sehner and the island surface. These are both minima, local minima of the area functional. And but one grows linear with time and the other one is constant.
Thank you.
Can I still go on for a little bit? No, I wanted to tell you about the gravitating baths, right? That's really the whole point of our...
Yes, of course.
Yeah.
Of course.
Yeah, you can ask yourself, what happens if I put gravity back in the bath? And now I go back for Sunday, we are going back to RS1. If I want to have gravity in the bath, all I need to do is I take the CFT, which was living on half space, and I put a second brane over there. Now I have two RS branes. And the one I drew in these pictures, or no, Mark drew in these pictures much closer to the boundary. What this is telling you that the closer you are to the boundary, the weaker the Newton is. So this is kind of trying to mimic that you have this physical brane as before, with a black hole on it. The green dashed line is my RT surface. Right now, this is just no black hole yet, right? This is still empty ADS. We don't have a black hole yet. We have some radiation region in this gravitating bath, and then we have associated with it an island region on the brane. Okay, so let me go through these comments here. So we added a second brane that brings back gravity in the bath. This time we have one massless, one massive graviton. And the dual descriptions in terms of a 3D CFT living in this red defect. So I no longer have a B CFT, I literally just have a 3D CFT. That 3D CFT has a conserved stress tensor. Therefore, I have a massless graviton, but that massless graviton is sort of split between the two branes.
Okay. So one question, Andreas. So how is it that as θ2 goes to 0, the stress tensor generates non-zero anomalous dimension? It seems a it's a weird kind of...
It's discontinuous. The θ2 goes to zero limit is not right. Whether gravity is dynamical or not is a yes/no question. Whether in your percenticle you decide to integrate over all metrics or not, that's like either do or you don't. G Newton can get dialed continuously to 0, but whether you study a theory of quantum gravity or whether you study a theory of fixed background metric and the CFT.
Sorry, I don't. Why is it an yes/no question? I mean, the G Newton can be as weak as you like, and then that should model rigid theory, right?
But no, whether you're in your percenticle, whether you integrate over all metrics. So what are the observables in the theory changes completely, right? If gravity is dynamical, you can't define, all observables have to be diffeomorphism invariant. You can't define any local correlation functions. The sort of things you would define in the CFT are no longer good observables in the theory where the CFT is coupled to the dynamical gravity, irrespective of.
I see. Okay.
I mean, the massless 4D graviton will be coupled to a conserved stress tensor involving
right, which is the massless 4D graviton couples to the 3D stress tensor on the red dot, which is now conserved because it doesn't have a 4D CFT anymore to talk to. Okay, here's you can say this might be a complicated calculation, but really all it boils down to is the following. Because I put in the second brane, now both endpoints have to be dynamically adjusted. That's basically the core of the entire calculation. Before, what we did is we held the endpoint of the radiation region fixed, but we had the endpoint on of the island adjust to minimize the entropy. Now both happen in a theory with dynamical gravity. It's related to what I said before. In a theory with gravity, you can no longer say I want to calculate the entanglement entropy with everything that lives at x being bigger than 5. That's no longer consistent. That's not diffeomorphism invariant. You can just only ask yourself, will I allow myself a radiation region and an island region? I want to ask myself, what happens if I let this entropy minimize? Both the radiation region and the island region can adjust where they're living.
No, but sorry, Andreas, sorry to interrupt, please excuse me, but how do you even ask the question? Because both sides have gravity. How do you even specify one of the two endpoints now in a covariant way?
So I specified, both of those endpoints have to find a location at which they minimize the entropy, right? And the answer where they end up is really simple. This whole surface just falls down and you get S equals to 0. So if you tell me you don't know where they should end up, that's very consistent. They just don't end up anywhere. You just get S equals to 0. And you could have said that should have been obvious to you to begin with, because now we are just starting a 3D CFT. Right now there's no black hole. We are describing a pure state in the 3D CFT. Obviously that should have S equals to 0. That's what the...
Okay, no, but allow me to register slight dissent. I mean, if I'm in asymptotically flat space, there should be a way, maybe you and Surat will disagree, but there should be a way, at least far away near asymptotic infinity, to be specifying the region I'm interested in a generally covariant manner, no? As in I shoot in I'll have to think about it, but I shoot in geodesics or something from a region which is experiencing some gravitational force, which I specify and say, this is what I mean by
There's some more coarse-grained quantities, which, there's been papers have been written by Shalom Key and his collaborators, but that will not give you a fine-grained definition of the entanglement entropy. You cannot define meaningfully an entanglement entropy of a region in quantum gravity, because you can't have a diffeomorphism invariant way of defining it.
Andreas, sorry, just to understand, your green curves that are going down are computing the entanglement entropy of what with what?
Right, so right now I'm calculating, the dual description right now from the CFT point of view, all I'm having is a 3D CFT. I'm studying the ground state of the 3D CFT and I'm calculating the von Neumann entropy of the ground state of the 3D CFT.
Okay, so right, so it's just the thermal entropy.
Not even thermal, right? It's just right now there's no black string.
There's no black. Once you put in the black hole, it'll be a thermal entropy of this 3D.
That's right. Once I put in the black hole, I get the thermal entropy. Right now I get 0, and that's obviously the right answer, because
so it's not really an entanglement entropy of anything with anything. It's just
that's right. That's right.
Okay.
Maybe from the 3D point of view, it's not the entanglement entropy of anything. From the 4D point of view on the branes, this is exactly the calculation we studied before. It's the entanglement entropy of some radiation region in the Bass brane, which you kind of try to define to separate the Hawking radiation that came from the physical brane over to the Bass brane. But if you try to do this, you find, because you put gravity back in the brane, the radiation region adjust itself so that the answer is 0.
But aren't you saying that in this question, in this setup, there's no precise question to ask, and therefore there's no interesting answer to get?
That's basically, yes, the question you try to ask, the way people set up the page curve calculation doesn't work if the Bass is gravitating. It's basically, you can phrase it like this, right? The page curve calculation crucially relies that you have this non-gravitating region in which you can separate the non-gravitating region into like R and not R. You can no longer do this when you have a gravitating Bass.
Yeah, thanks. Thanks.
Well, let me say this. You see, from your red dot 3D CFT, you are simply computing the entropy of a pure state, it seems to me.
Yes, that's what my slide says, right? It says, obvious from the CFT point of view, I'm calculating the entropy of a pure state.
But you know, there are well-posed questions, even in a CFT, which will give you non-trivial answers. This can be illustrated very clearly in zero-brain quantum mechanics. If you ask the right kind of question about...
Yes, and I'll ask other questions in a second. Let me go on, then I ask...
fine-grained entropy questions. They're not coarse-grained entropy questions. They are fine...
So the question that... The analog of the question that people ask in the context of the page curve gives me 0 as the answer. This is exactly the same question people try to ask before it gives me 0. You can ask other questions, I'll ask other questions.
So what I said was from the 3D perspective, but let me reiterate from the 4D perspective. It just seems to me that the main issue is how do you demarcate in a generally covariant manner in a theory of gravity, some region whose entropy, fine-grained entropy you might be interested in. Now, is it clear that that question is meaningless, even if I try to construct a region very close to the boundary? Maybe it is, but is that obvious to begin with? I can certainly demarcate regions in a semi-classical theory of gravity where quantum corrections are small in a generally covariant way, right? Like I'm sitting in this...
I think that the obligation would be on your side to show that you can do this. I think standard wisdom is you cannot do this, right? I have a diffeomorphism and my gauge invariance. I cannot define for you the entanglement of the region in a gravitating system.
Well, okay. Well, I think there are precise questions you can ask from the 3D CFT point of view, okay? And I would like to suggest a 4D version of those questions. And they're not coarse-grained entropy, they're fine-grained entropy. And I think it's questions like that which would be the analog. But okay, go ahead.
So I have one question also. So
can I say something? Just to say, so Andreas, I don't know if he's included in the talk, but there are certain other questions here one can ask which are fine-grained questions which do give non-trivial answers. But the question is, if you include all the degrees of freedom on this region R, then is there some sense in which you can demarcate, the degrees of freedom from R from its complement? I mean, in the prescription that you and Sumit and others had, as we discussed, you also had to throw out some operators, right? You had to throw out these integrated metrics and so on.
You have to throw them out, but I think it's versions like this which are the precise versions nonetheless. We may not have the ultimate word, but I think there are precise versions like that which should capture some version of your
So I think that's also true of the Shaolang key and so on prescription. If you start throwing out operators, there might be some way in which you can discard degrees of freedom to get something. And that's the sense in which we're saying coarse-grained entropy, because you're not really including all the observables that live on R. You're trying to come up with a truncated list of observables and then say, let's define the entropy with respect to that. And then it's fair to ask that kind of question.
In flat space, for instance, I think it may not be a fully fine-grained description. What one is computing. For instance, Shaolang key, that's just the standard thing of putting a cutoff like Gibbons and Hawking, right? So and finding a background subtraction. So, but that kind of calculation, it may not be a fully fine-grained description, but I think there is some sort of a approximate fine-grained description or something where the radius of the cutoff actually somehow plays into a role, but I don't think anybody has made it precise. So it may not be the exact comparison with the ADS. But it's something intermediate in some sense, where the cutoff radius plays a role in the coarse graining scale or something like that. Because so another thing, so I would have thought that if you in your prescription in this around the red dot is probably where something similar can happen, because that seems like the asymptotic region to me in your description, not the
yes. If I go to my next slide on it, this was something like global. Let's not talk about global. Let me quickly bring back in the black hole, and then maybe we can some of these questions become clearer, right? In order to go back to kind of study page curves, we want to bring back in a black hole, which is now this black dashed line is the black hole horizon. So this goes back to something I was asked earlier. If you want to hold the bath at a finite temperature, that's now a problem because there's gravity on the bath too. So you can't just put in a finite temperature and expect nothing to happen. Gravity will back react. But one thing you can do is put a black hole both in the bath and on the brane. So this is to get this black string configuration, this black dashed line is a horizon. I put a black hole with the same temperature on both branes. And in this case, the same procedure where you have to adjust both the island and radiation region has the RT surface fall down until it hits the horizon. And now the entropy will be a thermal entropy like Shiraz asked before, but it will again be completely time independent. When you get a flat page curve, very much like what was conjectured to be the case in asymptotically flat space. And here the point is that very much like in flat space, you have a region, in this case is this red dot, where the entire quantum state of the bulk can be obtained by studying the CFT on the red dot, maybe including its thermal field double, but you have an exact quantum description for the entire space-time. All information is always accessible to this like one part of space-time where there's no gravity, which is the 3D CFT, where the two 4D gravitating regions meet. It's something the chat. Oh, Surat is helping me. Wonderful.
No, sorry, I was replying to Shiraz. I replied to everyone by mistake. Sorry. Sorry.
Now I got stuck again. Why is this happening? Oh no, yeah, something moved. Right, this is what I just said. The entire quantum information about the bulk is contained in this non-gravitating defect. And that's sort of the analog in the setting of the past of null infinity in flat space, where you can kind of obtain the entire information that of the full quantum state in your system.
Yeah. But I mean, in a sense, sorry, but in a sense, the summary of, please don't mind, but the summary of your past few slides is in the 3D CFT, the only meaningful question I can ask is trace rho log rho for the full rho. The full rho is a pure state or a thermal one. I'll get that answer. If it's a pure state.
Yeah, I didn't say it's the only meaningful question. I think that's the question, that's the analog of what people asked before.
Okay. But this is the resolution of the information puzzle. I mean, I just, sorry, but okay.
Here's maybe addressing what you read. They are right. While we believe that the zero statement is kind of is the relevant statement if you want to ask yourself, what happens if you bring gravity back into the bath? The page curve disappears. The full fine-grained information gives me a constant page curve rather than a page curve that goes up and goes down. But in the same setting, you can ask other questions. You can ask other questions and they still give you a page curve. And what you can ask is what happens if I want to calculate something like a left-right entanglement entropy, where I go in and say in this 3D CFT, I can internally divide the degrees of freedom that belong to the left brane and the right brane. And technically the way you define this, you take like the 3D CFT, you open it back up to like a little 4D interval with like two 3D boundaries that allows you to separate degrees of freedom according to like the left brane and the right brane. And in that case, you get two types of RT surfaces again. You can get something like the Hartmann-Maldacena surface, which goes straight down and hits the defect on the other side of the Einstein-Rosen bridge in the thermal field double. But we can again island surfaces where kind of the island surface of the nearer brane, the more strongly gravitating brane wins. And then again, you can basically, depending on the angle of the brane, one of those is the right answer. But in this setting, you're going to get a page curve, at least for the details depend on the angle of the brane, but there are questions you can ask about the setting where you do end up with a page curve, but these are sort of more coarse-grained quantities because you're asking kind of, you're throwing away some of the degrees of freedom within this 3D CFT. You're asking about the entanglement between like the degrees of freedom which you divide by some sort of extra internal structure, which allows you to throw away half of the degrees of freedom of the CFT. So there are questions you can ask which do give you page curves, even in the setting with a gravitating bath. But the original question, the question about what's the entanglement entropy of a radiation region in the gravitating bath, gives you a constant page curve. And that's
have we put in a black string? What is the, I didn't quite, maybe I missed the one previous slide. Can you just go back to the previous slide? I didn't quite understand the setting. So this, is this black dot horizon? Black dash?
Black dashed line is a horizon. So there's an analytic solution which you can write down with two branes and a black hole where the horizon is this black dashed line. This is known as the string solution, which has like a black hole on both branes.
So now the situation is quite different from the standard island computation, right? Because now your R region is in a very gravitating part. There is a horizon there.
Well, the R region doesn't, it inculcates a horizon, but I would say this is sort of the closest analog you can have to kind of keeping the bath at a finite temperature, right? My bath is a finite temperature. Either I need to put a cosmological space-time on that brane, but then I get time dependence. This is the easiest way of getting something static, where I basically say what is finite temperature bath, at finite temperature radiation in the bath does, it itself collapses into a black hole. So now I have a black hole both on the weakly gravitating bath brane and on the strongly gravitating physical brane.
Okay, yeah. So let me ask you the question this way then. So here, for instance, so this wedge is basically it seems like a compact geometry. Is that a compact geometry?
Yes, again, this is what I said before. Topology is like AD is 4 times an interval. That's kind of one way of understanding why you get a massless gravity.
So, and you're letting the dark green dot and the dark R dot. So are they both allowed to vary when you extremize?
Yes.
I mean, but isn't that the same thing as kind of like, if you kind of sort of decompactify this picture, isn't that like the same thing as, if you're looking at let's say a global ADS black hole, and you're looking at the RT surface of the entire boundary, and then you would find that the RT surface straddles the horizon. Isn't that the same calculation?
It's related, right? It's a different calculation, but it's, I mean,
so my thing is,
because you have the brane, you have this new language of talking about it, right? You're kind of having an radiation region in this gravitating bath, but that radiation region just doesn't want to be there. It wants to shrink to be just a black hole, so the RT surface becomes the horizon. I don't think you have that language. If you, in the calculation you just described, we only have global ADS with a black hole inside. You don't have even this. No.
Right. I'm saying that, but on the other hand, we don't say that calculation is, revealing something about the information paradox. So why is it that this setup, which seems structurally very similar,
because the setup you're describing does not have a description in terms of 4D gravity coupled to a bath, whereas this setup has a dual description in terms of 4D gravity coupled to a 4D bath, where gravity is both in the bath and in the physical region. I mean, you don't have that second dual description in the case you're describing. In the case you're describing, you only have CFT and bulk description. Here you have still 3 dual description. You have 3D CFT, you have 4D gravity on 2 separate universes talking to each other, and you have 5D gravity. It's this in-between dual description that allows you to know why this setup says something interesting about the information paradox. If you ignore that middle description, of course, you have nothing to say. But that's the whole difference between just global ADS and the setup, that you have this in-between description.
Yeah, Andreas, just to understand your, I should have, but I slightly have lost track. Your 2 branes which have gravity and so on are in ADS space, ADS4, if I understand.
The world volume series, like, it's an ADS4 Schwarzschild black hole. So I have 2 branes, each of them has an ADS4 Schwarzschild black hole, and they're communicating with each other via their common boundary.
Right. No, where I was going was, just allow me to say the following, then you can jump up and down on me. If we really want to solve the information puzzle, at least I feel we have to try and answer Hawking on his terms, but perhaps making some of the points more precise. Now, Hawking's point was simply the following. He said, if I paraphrase, there is a sense, reasonably precise, but not fully precise, I agree. There is a sense in which you can talk about the region sufficiently far away from the black hole. Okay, this is because gravity is weak in that region, etc., etc. And just as I can talk about this room in which I'm sitting, I can talk about that region. Let me collect the radiation which reaches that region. It looks thermal. Okay. Now, if we are going to try and ask and say, no, we can do a precise calculation and show to you that it's not anywhere near thermal. Okay. I think we do need to try and ask, is there a sense, maybe slightly coarse-grained, in which we can make the region sufficiently far away from the black hole kind of precise after some required coarse graining, and then compute that slightly coarse-grained version of the entanglement entropy. This is what
I'm not claiming that I can answer that question at all. No. Maybe I should say, what do I think I learned from this calculation? I think what I learned is somebody calculates for you a page curve of a theory of gravity coupled to an external bath. They're having a correct calculation, but it has nothing to do with Hawking's original paradox, because that page curve that they get in this case, they introduced by hand by coupling to the non-gravitational bath. It's a non-gravitational bath that gives them the page curve they're calculating. They're not calculating a page curve for the black hole. They're calculating a page curve for the non-gravitating bath. If you bring gravity back into the bath, that page curve completely disappears. So it's...
I totally agree.
The original phrase is the bath that gave you the page curve. The bath wasn't a harmless spectator. The bath is what gave you the page curve to begin with. That's the lesson I want to learn. And I don't claim that I have an answer to the question you were asking.
No, I totally agree. You've done a beautiful calculation. But where I was going with my question was maybe we can make some progress towards that question I was trying to raise in your setup. And I should shut up and let you complete your talk. But let me.
I think I'm done. I showed you this picture. There's a lot of beautiful calculations that go into this picture, and Mark, who did most of those, would be really mad at me for not talking about them. But I really like talking about our S-train. So all I have is like this slide where I say, thank you. This was all I had to say.
Okay. I'm sorry if, take your time. I didn't mean to.
Maybe we can clap first and then.
Yes. Thank you very much, Andreas, for a wonderful talk. Yeah, let's have some more questions.
Now, just to come back for a moment, then others should say. But my question was, Andreas, okay, in a sense, let me ask it, in case we had asymptotically flat gravity on your brains, okay, somehow, and then we can come back to ADS. But suppose you had asymptotic 4D gravity on your brains in a setup where you had embedded things in 5D. Now I can take the view that at least I can go, I have some black hole and so on in the center of ADS of asymptotically flat space on the boundary, and I can go sufficiently far away from that black hole and locate some region in the same spirit as Hawking would have done. And I try to anchor the ends of my RT surfaces there. I agree it's not 100% precise because it's a theory of gravity and I'm specifying the region maybe by some area of a sphere very far away from the black hole, but I'm willing to for a moment live with that kind of imprecision. And if I do it, what answer would I get then? In other words, the beauty of your 5D embedding is that things become classical, and I might be able to raise the imprecision required in a more
right. So doing this with critical brains is very interesting. There's actually somebody on this call here, Chetan here, he wrote a paper on this. So I have very little to say about what happens if you do asymptotically flat space rather than ADS4 space. The system becomes more complicated to study because you have to somehow deal with this back reaction that the brain will start moving, but you should ask your local colleague or your I guess your neighbor from Bangalore rather than me. I don't know what happens.
Could this be related to the fact that, even infinitesimal weak coupling to gravity, you said it changes the dynamics of the boundary completely. It does not let you anchor the RT surface anymore. Right?
That's what I would say.
So this is what I was talking about. A very small change. Newton's constant going very close to zero is like a discrete change. You said. I think this is related because one should be able to think of very weak gravity as a rigid theory.
But Abhijit, all I'm saying is, it's not as if Hawking's question was meaningless. Okay, just because we have weak gravity in the room I'm sitting doesn't mean there is no clear sense to the fact that I'm sitting in this room and I'm far away.
Yeah. That's what I am saying as well. Yeah.
Right.
Yeah, I agree.
You're asking, when you say it's not meaningful, we keep saying this intuitively. What that means is that, there's a sense in which you can compute maybe 2-point correlators or 5-point correlators in this room. And those correlators are not affected by the fact that there's a Sagittarius A star sitting somewhere in the middle of our galaxy. But, if you start asking questions about the entanglement entropy of this large sphere that you're looking at, this entanglement entropy is an extremely fine-grained quantity. I mean, remember, it can distinguish between a thermal state and a pure state, even though those states are not distinguishable by simple correlators. So, you know, entanglement entropy is not the kind of, you know, you're using intuition from low point correlators and then insisting that it should go over to entanglement entropy, but that doesn't.
No, I'm not. What I propose to do is the following. Using, if you like, low point correlators, let us come up with some notion of approximate fine graining. You know, that is to say, there is an approximate notion of locality which comes with
Yeah,
a
that's what I would say.
point correlator. Now, use that notion to ask how much can we make, using that notion, can we make precise a question of how much von Neumann entropy there would be in some region? I think there might be a way to make progress on this question. Okay.
I think even on Scribe Plus, there is a way to do this. I mean, you know, which we actually discussed in the original paper as well. You know, you can throw out systematically certain components of the metric. And if you do that, you do expect, at least, you know, under certain assumptions, some kind of page curve for the radiation on Scribe Plus. But that happens after you throw out certain components of the metric.
Certain components means one component, right?
Yeah, you have to throw it out at every point. Yeah, so you throw out at every U. You have to throw out. Yeah, I mean there are only 3 components.
You keep all the news curves, all the news operators, but you throw out just the mass, right?
Well, you have to throw it out at every point. So I mean,
I understand.
Two operators and one mass. So you throw out one of the 3.
But you're keeping a lot. You're keeping everything that a radiation observer would say.
Yeah, and you throw out the mass, correct? But it's, I mean, I'm just saying there are a discrete number of components of the metric of which you throw out one. I mean, there are 3 components of which you throw out one in some gauge. So, anyway, but can I just say one thing, Sandeep? But you know, the thing is, if you throw this out, you will get a page curve. And if you insist that you want to see that, you would see a page curve. But the real question is, why is this a natural thing to do? If you're an observer far away, you can measure one component as well as any other component. So, you know, I mean, one could do, if you insist that the answer is a page curve, you keep the answer fixed and change the question, then there is a question one can ask.
You know what? Now I have to understand better, although I should have, the component you're throwing away. But what I'm trying to look for is some approximate notion of fine graining, if not exactly, which corresponds to an approximate notion of bulk locality, at least far away. Then what one would like is a calculation, an approximate calculation that shows the entropy going up and up as per Hawking, and a refined calculation which shows it coming down. If something like this can be done, I would say, okay, we made progress towards understanding the black hole question. Okay, don't mind my putting it like this. Now, my question is to you if you throw away these news operators, if I understand,
throw away the others. Keep all the news operators.
I see. I'm sorry. Keep the news, throw away the others. Is there a sense in which, you know, Hawking's original calculation shows the entropy going up and up, and a better calculation shows it coming down? Okay, that's what I would like to ask. There is clearly an approximate calculation Hawking does in some way, which shows the entropy going up and up. That should be the starting point. Then can it? Okay.
I think you're asking for a third requirement. You're asking, of course, there is a sense in which you could take news operators and then say, let me restrict myself to 20-point correlators of news operators. So I won't even consider all point correlators of news operators. And then the calculation would just go up and up, and that's really what we call the thermodynamic entropy. It's really coarse-grained. And then it would go up and up like Hawking's calculation. And then you could start including more and more correlators of news operators. And then at some point you would see the page curve. But in all of this, you know, it's still fundamentally constrained because you didn't keep track of one other constrained degree of freedom. So
yeah, I had a question about this picture.
Go ahead.
If I can. So in this picture, so if the black dashed horizon was not attached to the theta 2 brane, then I think it would be a little bit more similar to the calculations that people have been doing, and there will be a gravitation on the sink, and also and I think this is a way in which also one can separate the connection, you know, whether there is any significance to the mass of the graviton, and whether the gravitation on the brane is what is significant. Because but I think you will have to solve PDEs.
Yes, because it will become time dependent, right?
Exactly. Yeah.
Our simplest way of getting something that we thought is close enough to the situation we want to. you come up with a new time-dependent gravitational background.
Right, and I think that the current setup, it's not what you're somehow. I feel like you're saying that there is no information paradox rather than there's no information paradox. This calculation resolves. I would say. Would you agree with that? There is no information paradox is your answer in some sense.
Yeah.
Okay. Fair enough.
So just to follow up on perhaps the kind of things.
In this calculation, the one that I didn't really talk much about, here you would have an information paradox if you calculate the left-right entanglement rather than the entanglement of a radiation region. So you calculate the entanglement entropy when within this 3D CFT you separate degrees of freedom to the left and right degrees of freedom, or roughly speaking, if you calculate entanglement entropy you get when you trace out one entire brane and keep the other entire brane.
So this
you have.
So the left-right means is it so you're basically using the vertex? Is that the?
So I have this 3D CFT, but I can separate this 3D CFT. It used to be like two boundaries of 4D intervals. So I separate basically degrees of freedom associated with one boundary from the degrees of freedom associated with the other boundary.
Okay.
Sorry, Andreas, just to follow up on perhaps the spirit of Sandeep's question, in the thing about your five-dimensional setup is that its boundary is three-dimensional, and therefore there was no question to ask, right? Whereas the thing about a gravitational radiation in flat space, let's say you take a five-dimensional flat space, the boundary is four-dimensional on Scri+. And so naively there is a question to ask. Right, you could naively ask about the entanglement entropy of the early and the rate, of one part of Scri+ and the other. And that seems sort of similar to your splitting up of your 3D boundary into two parts. So it's so
my understanding is you get a similar answer in that case, right? In that case, you get a page curve back. That's I think what Subrat.
What I think Subrat will want to say is that if you ask that question properly, you won't get a page curve, but if you ask it in some slightly wrong way, you'll get a page curve.
In a coarse-grained way, we don't call it wrong. It's like a slightly coarse.
Fine, exactly. But it seems to me that in your setup, it was clear from the dimensionality that there was not going to be a question to ask. Right?
And
so,
here, I show you here's a question to ask. It's a different way of slightly coarse-graining, where I throw away half of the degrees of freedom on my 3D CFT.
No, but there's no analog of what you would call a good question, a fine-grained question to ask, right? On the other hand, in the asymptotically flat space case, though Subrat has given powerful arguments, a skeptic might still think there is a fine-grained question to ask, which is giving the entanglement entropy of one part of Scri+ with the other. So that is not addressed here because the dimensionality was different.
Right. So you would be saying the analogy is perfect, right? The fact that for him the non-gravitating region is like Scri+, and for me it's just some boring three-dimensional.
Yeah, I'm saying that there was nothing to divide in time. So there was.
So what you're putting too many words into my mouth, right? What my original goal was that I set out to you is kind of asking what happens if you put gravity back into the bath in this calculation of you calculate a page curve in ADS coupled to a non-gravitating bath, and I think the statement is still that the page curve disappears if you put gravity back into the bath. And you tell me this was sort of obvious because I threw out the baby with the bathwater, and I would completely agree with you. But now you're asking is this kind of how much can you learn from this about asymptotically flat space, and then I'm not quite sure.
Yeah, perhaps I could ask the question. Suppose for your fine-grained question, suppose you got any answer but the one that you did from your bulk calculation. Wouldn't that just be an inconsistency?
Right. Yes, that's absolutely true.
Okay, so then that didn't really need a calculation except to check the consistency of this RS way of thinking.
That's right. I mean, it's sort of trying to understand what it means to bring gravity back into the bath and seeing that it means that the radiation region will adjust itself, and it will have to do so because otherwise you get an inconsistency.
Yeah, it's really nice to see it working in detail. But I'm saying that
in our paper, if you look at when we actually calculate things, right, getting this S equals to 0, which I made a bigger deal about in this talk, that's sort of like a very short calculation where you just say, well, that's the answer because what else could it be? The interesting calculation in our paper where we actually do work is getting the page curve for this kind of more coarse-grained question where we calculate left,
And
right.
what is the lesson from, what is your takeaway lesson from this more complicated calculation?
This is a beautiful calculation because it kind of has a lot of interesting structures. Things depend on the angle, but I'm not quite sure what the takeaway lesson is. I thought the takeaway lesson from the other part was more obvious, that putting gravity back into the basket gets rid of the page curve.
So can I propose a takeaway lesson which might be happy, which Shiraz might be? I think actually Andreas said this. I think one takeaway lesson from this is that the page curve always answers a non-gravitational question. In that, in this last slide that Andreas had, where we do see a page curve, it's kind of a place where, we're asking a question on the red dot where we switched off gravity. So here and in the page curve computations that people have done, and also in this other Scri+ thing where you throw out, the component of the metric that imposes the Gauss law, you're kind of consistently asking a non-gravitational question. So one slogan, I mean, I'm not saying this project slows it, but one possible slogan, maybe it's too ambitious, might be to say that the page curve is kind of inherently asking and answering a non-gravitational question, which may be a slogan one could put to this last slide as well. Which is it's a very beautiful page curve, as Andreas said. But it's kind of a curve where, we ask a question about the two parts of the red dot which are not gravitating.
I see. And you say
I don't know if Andreas agrees with that. Sorry, yeah.
I agree with that. Yeah, no, I rarely disagree with you. You just always say it much better than I do.
I see. And you say that you're saying it's like a non-gravitational question on Scri+ because the constraint equation is being, the quantity that appears in the constraint equation is not being considered.
Exactly. So you're kind of choosing to throw away information about the Gauss law. Exactly. And here as well, in this case also you see a page curve. So if you try and ask a gravitational question, it's hard to get a page curve, but you somehow find a way to get rid of gravity and then you see a page curve.
Yeah, but I might have thought, naively, you might have thought you could reach another conclusion, which is once you take this 3-dimensional boundary and make it a small 4-dimensional region and start dividing it up, you do see a page curve, right? So you might have thought that the analog of that in flat space would be you take Scri+ and start dividing it up and you will see a page curve. That might have been another natural analogy lesson.
But you divide it up in a non-gravitational region, no?
Even Scri+ is non-gravitational.
Yeah, but there's a Gauss law constraint that you're imposing on Scri+, which is important. Here there's no on this boundary. If you take these defects and you separate them, which is how Takenagi says it, there's no Gauss law constraint in the states.
Yeah.
But maybe this also answers the question Abhijit was asking. When you take G goes to 0, you have to still be careful of imposing the Gauss law. I mean, as all of you know very well.
Yeah, but Subrat, we ignore the Gauss law by saying that one operator that you would solve for by using the Gauss law is not part of your observables because you've solved for it.
Yes, you could say that.
So then it's not really ignoring Gauss law.
But that's like saying that you can't measure the electric field at one point, right? Because you'd say that, I solved for some operator in the Coulomb gauge and now the electric field is not an observable because, I'm not allowed to measure it.
Yeah, I'm just saying that we're not ignoring it in the sense that we're not doing anything wrong. It's not keeping states that don't obey the Gauss law.
Yeah, you look at those states, but as you say, you choose to not look at the electric field or not.
I understand. I mean, and you made great points on this, but I'm just saying that the analogy. Okay, fine. I'll stop. Yeah, right.
But so one question about this slide. So you say that in this slide you take the 3-dimensional boundary and you split it into 2 with a 4-dimensional interval. So first of all, I don't understand how does one divide a CFT into 2 degrees of freedom? I mean, presumably, perhaps what you are doing is coupling them and and then a new CFT results or something like that.
And so the way the 3D CFT living on the dot, the way you can think about the 3D CFT on the dot, you you can do this with like supersymmetric series n equals 4 supermills. And you have 2 boundaries which kind of have like a stack of NS5 branes. So you have like the boundary condition is highly non-trivial, right? You have 40 n equals 4 supermills coupled to like a complicated 3D CFT on 2 ends. And that is sort of that at low energies, this is governed by 2 3D CFTs because they kind of, the 4D CFT gets sort of gapped by sitting on the interval. Or in any case, you can arrange the 3D CFTs to have much larger degrees of freedom. But you can still separate now spatially, like you would always do in a CFT. You say, let me calculate an entanglement entropy where I define like a separating surface that separates the left defect from the right defect. So the low energy CFT that you get this way, where you take like these 2 boundaries and you kind of then shrink the interval to 0 size. There's sort of a way of, by position in this 4D space, separating degrees of freedom, the left degrees of freedom and the right degrees of freedom.
Right, but if you now look at let's say gravity that is dual only to the left degree of freedom, that will turn out to be massive, right? Because the coupling would give you some anomalous dimension.
Right.
So
if you look at what's happening here, there's like the graviton on both branes is massive, but these are also not really eigenmodes of the mass operator. The eigenmodes it's like we have like a double well potential. If you look at the modes which have a well-defined mass, there's a graviton which is mostly peaked on one brane. There's a graviton mostly peaked on the other brane.
Right.
But the massless mode is some superposition of those, and the massive mode is also superposition of those.
Right.
So you have a massless graviton which is sort of shared.
But the issue that was present in the previous computation will be there in that the Hawking radiation is happening on in a massive gravity theory, right?
Yes.
Okay.
So when I said the mass is important, what I really mean by this is I think the coupling to the bass is important, and the coupling to the bass is what gave you the page curve to begin with. If you take away the coupling of the bass, then you take away, either take away the coupling to the bass or take away, make the bass gravitating, then you lose the page curve you originally had. The mass was just a symptom of this. The mass is kind of telling me, I tell you there's something really happened to the system. I couple to this external non-gravitational bass. That was crucial for the page curve.
No, but ideally, the way you want to ask the question is you still want a massless gravity with the ability of separating some degrees of freedom, right? The bar degrees of freedom and the degrees of freedom that are dual to the gravity.
You're saying this calculation, I get the page curve back, this doesn't really do this yet. So you'd like to see a page curve as a graviton, and you say this isn't a page curve for a massless graviton. I think
Right. Okay. Thank you.
Just one last, thanks, Andreas. It's been a beautiful presentation. Thank you so much. But just one last thing, which is, to go back to what Shiraz was saying, and Subrat has, of course, been teaching us, is somehow what one would like is, at least for me, is if we are going to have to coarse grain a little bit to understand Hawking's result in the first place, is a notion of coarse graining which is related, as I was trying to say, to some notion of approximate locality. Because in the end, what he was trying to say was, let me gather the radiation sufficiently far away from the black hole. It looks thermal. And this is what we've been trying to do in these papers, very beginning papers. I don't think we have the last word in it. But Subrat and Shiraz, is there a sense in which you can translate a sort of notion of approximate locality far away from the black hole to something you would do on scry plus and scry minus, in terms of not the full set of operators you may keep, but a smaller subalgebra? Is there a way to do that map? And then just to complete, if we can achieve that, it may be slightly imprecise, but if we can, and we see the page curve going up and up as in Hawking's calculation, then it could be that there are one of two answers to Hawking's question. You try to do precise calculations, but it still goes up and up because what you're computing is a coarse-grained quantity tied to approximate bulk locality. Or it could be that you do a more precise calculation and it comes down. Okay, either way, I would say I sort of get a better understanding. Okay.
So I can make one comment about this. I think if you do a calculation with two cutoffs in flat space, it might be possible to relate the coarse graining scales.
Okay.
Two cutoffs means two separate cutoffs and try to relate them. I mean, I have not pushed it too far, but I have a suspicion that might be possible to relate the coarse graining scale, even though it won't be a very precise statement about what the, I don't want to say too much because it is probably only partially correct. But so I think that there is a sense in which the size of the cutoff is somehow connected to the fine graining, the level of coarse graining in the fine graining, so to speak, in the calculus.
So I have an organizational comment. It's probably midnight or past that for Andreas.
Sorry.
So I think we should,
It's 10:30. Don't worry, it's 10:30.
Oh, okay.
Because I'm still in Seattle.
Okay. As long as he's happy, I was thinking we could release him if he needs to go.
I keep up Subrat like every Monday and Friday to like 11 or 11:30, so I think he deserves to kind of.
Okay, maybe a couple more questions and then we will stop.
No, just if you'll just permit, just to understand Chetan, then others should, of course. Chetan, this, what was this cutoff in flat space you mentioned? Just in
So I think I was just talking about this paper that I think somebody mentioned, this Xiaolang Qi and Shi Dong and a few other people who had a paper on introducing a cutoff in order to define entanglement entropy for gravitating systems, where so you, essentially, I don't think that it's a Euclidean calculation. And it's basically what they do is they subtract, it's essentially the Gibbons-Hawking idea, which is that you have a cutoff, you compute some quantities, then you subtract out the thing and so on and so forth. So that's how they define the entropy.
I see.
So what I was saying that, I also had a paper, it was in Lorentzian signature, which was, which is a little bit different, which is, again, introduces a cutoff. But I think the question that all of them kind of miss is that the question of what is this cutoff really doing as far as the coarse graining or the level of fine graining in the entanglement entropy that one is computing. And I think it may be possible to discuss that by introducing, multiple cutoffs in flat space and seeing maybe some suitable quantity, how does it change as you slide the cutoff. So, I mean, I have only, I have not really been able to pursue it too much, but I think there is some promise in that way of looking at things. And that might actually tell us whether it is actually a, fine-grained, what is the level of fine graining that is introduced by this cutoff. So that's, so that might settle it to some degree. That's it.
Thank you very much.
Can I just make one more comment, Sandeep, about this? So, there's one thing, of course, you could do, as we discussed many times, you go to Scribe Plus but throw out some constraints. But there's another thing which I think is more of the kind you want to do, which is you take some large region around the black hole and you try and define some notion of local operators. So you don't really go infinitely far away. And of course, there is a sense in which you could take like 10-point correlators or 20-point and define some entropy. I mean, in this paper with Sudeep, we tried to have some definition of an entropy of that kind. And we probably do expect that, you would see Hawking's computation because that would be like a coarse grain entropy. But then you also want a notion in which you want to see a page curve. So you want some intermediate scale where you see a page curve coming. You don't want to go to the absolute fine grain region where you get 0, but you want to go to some intermediate region where you see a page curve coming. It may be something like this exists. It would be interesting. I think one setup which I've discussed perhaps with you and with Shiraz and so on also is looking at the small black hole in ADS. For a small black hole in ADS, clearly the boundary theory is just always in a pure state, right? Which is what we have here. So if you compute the fine grain entropy of the full boundary, you always get 0. If you compute a coarse grain entropy, clearly there's a sense in which, there's a quark gluon plasma which is formed and it thermalizes. But what you want is you want some intermediate region which is not going to give you 0, but which is going to give you a page curve. So you want some set of operators there. And that might be a more precise setup in which one could ask how that happens. And let me just say there's the following complication in doing this. Now, I'm not saying you should do it. The complication is as follows. If you take a lump of coal, you could have said the same thing, right? You could have taken a lump of coal in ADS and let it evaporate. And you could have said, if I take coarse grain, it looks like the second law holds and entropy increases. And if I take fine grain, it's always 0. But for a lump of coal, there's a sense in which you can increase the fine grain notion of your entropy, like make it more and more fine grain. And you can keep S constant and change the gravitational coupling. So there's a sense in which you can switch off gravitational effects while keeping the entropy of the lump of coal constant. And there is no such limit for a black hole. If you try and make, and there's no sense in which you can make gravity, because the entropy has a factor of 1 over g Newton sitting there. So as you try and take, g Newton to 0, the entropy goes to infinity. So there is a sense in which black holes are kind of different. I'm not saying this is an insuperable obstacle, but there is.
I'll just take one comment there. It's that, so for instance, you just mentioned small black holes, right? So there are these papers by Berenstein and Hanada and people where they talk about small black holes in terms of submatrix deconfinement. So, and then you do have that parameter that you're talking about, which is m by n. That extra one parameter that you need is m by n.
N is the rank of the gauge group, is it?
And m is the rank of the submatrix. So, but it's not, I want to say that it is, again, that's many of those things are not completely watertight. People are not completely happy, but at least schematically there is a way out. That's all I'm saying.
Yeah. No, I'm in touch with Hanada. They're trying to simulate some of these notions of target space entanglement reformulated, partly with a view towards testing some of these things in terms of what does it translate to sometimes in a fine-grained notion in terms of subalgebras. Okay, anyway, but thanks for that comment. Yeah.
Okay, I think we should perhaps stop, and let's thank Andreas again for a really wonderful talk and being so patient with all of our questions.
Thanks for having me. I'm glad Subhash prepared me for this. Otherwise, I would have been a little surprised, but it was.
Thank you very much, Andreas. Sorry